Look at everything he's private. That's yes, yes. Yeah, yeah, yeah. I said I got the so I got the exit flow.
So many friends here, and this is the beginning of FTPI marketing. We have Minneapolis is evaluating whether it's supposed to be here at the time of the year. Themselves is plus 20. Okay, so even for those of you who are staying for satellite meetings in convention center for the rest of the week, the weather will still be good. We do allow participants to interact speakers, but the task of the chair of every session is not to transfer topic or answer questions. So please answer questions if you have to, but try to answer if there is absolute need to answer, to ask a question during the talk. We'll have time after each talk for discussion. So request to all speakers 40 minutes total, which we anticipate will be 30 plus 10. Last thing I was asked to tell you that those of you who will go for dinner tonight, on the back of your card, there's another one with your name and circles of different color. You need to take it out because then people serving you will know what kind of food you order. Okay, with this, it's my pleasure to welcome Subir Sachdev as the first speaker of the workshop. And the title of the talk is Road Disorder in the Theory of Mathematics. Yes, your time. Oh, yes, please.
Okay, thanks, Andre, for this nice March meeting. Better than the satellite meeting, I think. Okay, so where's my icons? All right. All right. Okay, so for this audience, I probably didn't need to remind you what the strange metal problem is, but just a quick reminder before I get to that. This work is with many people. Ilya is in the audience, and Sergey is also in the audience. I don't know if anybody else is here. I think maybe Jorg will be showing up, possibly. And Avishkar Patel at Flatiron, and Peter Luntz is a postdoc now at Harvard, and another student, Alex Nikolenko, and we also have a collaboration with Jorg Schmalian and his postdoc, Davide Valentinis. All right, so the strange metal problem, this is a very famous plot, sometimes called the foot. This is an LSCO in a magnetic field, and where the superconductivity has been suppressed to 0. And what's plotted is the exponent n, which is the resistivity exponent. And in a Fermi liquid, it would be 2, whereas there's this foot-like region where it seems to be 1. And this is fairly universal. So here's another famous plot from Rick Green on the electron doped cuprates, where again, when just above superconductivity, and I think even below, but if you suppress this, it's n equals 1 over a whole region near some possible quantum critical point of antiferromagnetism, and then Fermi liquid behavior out right-hand side. All right, so I think we're trying to move towards an understanding of this data, and I'll present some ideas and what the current status is. But a common perspective has been that this is due to some sort of quantum critical point. So one simple quantum critical point will be something associated with symmetry breaking. So in this case, the Fermi surface is changing from a square-like shape to a rectangular shape, and then there's a quantum critical region which perhaps has failure. Another point of view, it is somewhat more exotic transition. Here's one proposal where you have a phase transition in a metal that's very exotic. It's a spin liquid with small pockets on the surfaces. And then here at some large doping, it's a large Fermi surface. So there's a Fermi volume changing transition, which is not associated with any symmetry breaking that many of us have studied. And in the single band model, it turns out to be described by some emergent SU2 gauge field and also some Higgs boson of field phi, which condenses in the exotic phase. Okay, so this is a very different type of transition, and really in a pure system without disorder, the theory of this transition and this transition look very different. Okay, but one interesting point is that if you look across the wide variety of strange metals with very different microscopic physics, the basic phenomenology of the strange metal is pretty much the same. So one of the messages of my talk is that we want to take these theories and add disorder. And when you add disorder, you end up with a theory which is pretty much the same for all of these different critical points, which are very different in the pure limit. But I'll just focus on this simplest example, but everything I'm going to say now, most of everything I'm going to say will apply also to the other more exotic critical point I just mentioned. So what is the theory of this critical point without disorder? Well, this has been studied intensively, starting with the work of Hertz. So you have a Fermi surface, a fermion psi, and then you have a scalar field for which you write down some Landau-Ginzburg-like action, where S is now our tuning parameter. And then you couple the fermions to the bosons by a Yukawa coupling with coupling constant G. So there's some form factors here, which I've just omitted, depending on the specific phase transition you're writing down. So now we want to put in disorder. And so we start to put in disorder everywhere, really, in principle. So the most familiar disorder is, of course, this potential disorder, which is the basis of the theory of disordered Fermi liquids. Another very common disorder is this disorder, delta S, which just you could think of as a variation in the position of the critical point from point to point in the sample. And then another disorder that will play a role in our work is this disorder in the Yukawa coupling constant. And this has only looked at relatively recently, starting from all the work on SYK and Yukawa SYK models. All right, and everything in blue are fixed random variables. They're just fixed, and we want to study the ensemble average of this theory. All right, so the point of view taken, well, first of all, if you can do a kind of a relevancy analysis, and from the Harris criterion, you conclude that the most important disorder is just the random mass disorder. So you really have to worry about this first. And indeed, there were many papers starting, I guess, in the 2000s that did that, including some by us. And I'll mention some of them later. They were trying to look at the effects of this and just found that the effects are very strong. And then people just kind of said, well, what more can we do? Anyway, so more recently, we took a somewhat different point of view, inspired by all the work on SYK type models. We said that, well, okay, if this is the most important disorder, let's account for it at first in a somewhat approximate way. We just rescale phi so that this becomes space independent. Now, if you rescale phi, then some of the other terms will pick up random contributions, but they're not as important, so let's not worry about it. But one thing it will do is induce disorder in G prime, even if that wasn't there to begin with. So we said, okay, let's just take this theory with delta S equals 0, and now just imagine that you can analyze it in some self-averaging way, like in some Yukawa SYK theory. And so you just go ahead and do that. There's no guarantee it's going to work because you're kind of, by this trick, getting rid of the most relevant term. But you might guess that this would work as long as the eigenmodes of this scalar field phi remain extended. So we'll look into that shortly. Well, anyway, if you go ahead and do this, you get, basically, it's just a matter of solving some Eliashberg type equations, Migdal-Eliashberg, I should say, and corresponding equations for transport quantities. So we did some of that, and you get results that are really very interesting and suggestively similar to experiments. So one very important fact is that if you look at the inelastic scattering rate of the electrons, you get marginal Fermi liquid-like behavior, but the marginal Fermi liquid behavior comes both from the non-disordered coupling, which we call G, and the random coupling, which we call G prime. On the other hand, if you look at transport properties, it only comes from G prime. And the transport properties then are precisely those observed in many strange metals, linear T resistivity, and also optical conductivity, going as 1 over omega. All right, so that, got us quite excited, and, it suggested that this theory where you really account for G prime in a serious way is on the right track. All right, so there have been other works which I'll now mention. There's a work by Matt Foster, I don't know if he's here yet, where they looked at more traditional, to this kind of quantum critical theory, diffusion or Altshuler-Aronoff corrections. And one of the things I found that the corrections are actually very singular. So clearly we do have to worry about these localization type corrections. And I'm going to argue that really, yes, it's true, you have to worry about such effects, but really the place where they come in most importantly is not in the fermion localization, but actually in the localization of the bosons. So that's the main point of my talk. There's also this very nice work by Erez, Berg, and Georg and others, where they postulated by hand, in a way, that there's some localized bosonic modes, otherwise known as two-level systems. So there's some random array of two-level system randomly coupled to fermions, and you do some kind of, again, self-consistent analysis of this model, and they find very nicely an extended regime of non-Fermi liquid behavior. Okay, so we're going to now address the same issue, but in the framework of our theory, where we are not going to put in these two-level systems by hand, but really try to see if they're actually there in the system that I've just defined. All right, so what we're going to do now is slightly different analysis, where we take the same theory. I'm still working with this theory here, actually this full theory, and I just integrate out the fermions. So I integrate because I want to really study what's happening to the bosonic modes carefully. So you integrate out the fermions and you get some effective theory, which is essentially the Hertz theory, where you've got this Landau damping for your scalar field, which now I'm going to assume has more than one component. That turns out to be quite important. And then this is the tuning parameter. Unfortunately, I'm calling it lambda now, not S. That's because the plots were made with lambda by Avishkar. Anyway, so the blue lambda is now also random in space. So what we're going to do, well, you have to really keep three important things into account. You have to keep the fact that the mass is random and really account for it exactly. You have to keep the fact that there's Landau damping, which we just approximate by a space-independent Landau damping, which should be okay as long as the fermions remain extended. And then you also have to account for the boson self-interactions, because that's really crucial in the regimes where lambda becomes negative. If this becomes negative, then the whole theory doesn't make any sense until you include this. So one of the method we're going to apply is actually very similar to what Adrian Del Maestro applied in one dimension for a slightly different problem, which is just self-consistent Hartree. So we're just going to solve the self-consistent Hartree equations, which are right here, but exactly in the presence of disorder in 2 dimensions. So basically, you have some renormalized mass at each point in space, lambda bar, and you have to determine lambda bar self-consistently because it also appears here where psi alpha are the eigenmodes of this quadratic operator. So just determine the eigenvalues of this, eigenvectors and eigenvalues, and then you self-consistently solve this equation. That's not so easily done, but Avishkar used modern GPUs which has finally been put to good use, other than in ChatGPT. And you know, for quite large samples, self-consistently solve this equation and develop some very nice methods for it. Okay, so this is the kind of results you get. So for example, if you look at the correlation length of phi, there's definitely a very nice crossing point, presumably at the location of the quantum critical point. Now what you do is you study these eigenfunctions. So these psi alpha are the eigenfunctions of this operator. And you study these eigenfunctions and look at how extended are they. So you measure the localization length of the eigenfunctions. So this is our main result here. This is a function of the energy of the eigenmode, and that's the localization length. So at higher energies, this region B, you see very extended eigenmodes. And so we might guess, well, the kind of self-consistent mean field self-averaging approach we've applied should work. But when you get to lower energies, you see very localized states, like in the region C. And now, of course, you know, this is a region where you have some region of negative mass, and it's really being very important to determine the excitation of this energy scale. And also then you see something rather remarkable. You see that as you go to even lower energies, the localization length again increases. So that's a question, the state of, in fact, we anticipated would, but let me present it as a puzzle that came up from the data. Why is it non-monotonic? All right, so to understand that, I want to recall some very nice earlier work by Hoyos et al., Thomas Voita, where they looked at essentially this model. This is a while back, 2007, with the Landau damping and a random mass. And they also added a random hopping term for the boson phi. And they looked at a limit where the disorder in S and J was very broad and very large. And they did some strong disorder RG, the so-called Dasgupta RG. And they found a remarkable result that the RG equations of that random mass Hertz model in any dimension are this for a system with continuous symmetry are the same as the RG equation for an insulator with discrete symmetry, which is the random bond Ising model, Francis field Ising model, which was solved exactly in one dimension by Daniel Fisher and also studied numerically in 2 dimensions. Okay, so one of the results of the random bond Ising model is that the localization, the size of the excitations becomes larger as you lower the energy. That's because you get resonance between localized states far away, and then they form a collective excitation under this strong disorder RG. And in fact, the localization length increases logarithmically with energy. And that's really exactly what we see over here. Okay, so we think this can be understood by this beautiful result of Hoyos et al.
Subir, what are units? What are units on vertical axis?
It's lattice spacings.
Thank you.
Yeah, I forget. So it's somewhere, I think I have some data. I think the system size will be, yeah, L is 160 by 160, beta is equal to 800. That's really pretty remarkable that Avishkar has been able to study such big systems and at such low temperatures. So here we compute the self-energy from these 2-level systems, if you wish. These are the overdamped localized modes. Just compute it perturbatively. And you do find marginal Fermi liquid behavior with X and N. Of course, in this region here, near the critical point, we understand that from previous analysis of extended states. But down here, we see what seems like a whole extended phase with this kind of nearly marginal behavior coming from these localized 2-level systems or bosonic modes. I should say that more formally, the overdamped localized bosonic modes. We can also compute the resistivity, although not in the same density of plot, so we can't make a color plot like this. Another nice thing about this method is that you can analytically continue to real frequency with exactly. It's no problem at all. And so you get linear resistivity here and Fermi liquid-like behavior over there. and also some residual resistivity. Anyway, okay. So anyway, we'd like to suggest that, although this is not certainly by any means fully understood, that this high temperature part here is really the physics of some self-consistent Eliashberg type analysis of a random Hertz model. The key thing, you have to put the randomness in the coupling, and then everything follows. And this foot here is due to some localized overlap bosons, but in a regime where the fermions still remain extended. And of course, this needs to be understood better, and how this crossover occurs. These are all interesting open questions, I would say. All right, how are you doing on time, Andre?
You still have 10 minutes.
Okay, good. So now, so that was a review of our and other people's work. So I hope I'm meeting the criteria set by Andre. Now I want to talk about ongoing and future work and mention some interesting questions, open questions. So first of all, quantum Monte Carlo. So this has actually been ongoing for a while by Avishkar Patel, Peter Luntz, and Michael Albergo. Hopefully the paper will be out soon. So basically they take a model of a spin density wave critical point, and then add in this coupling here, which is spatially random. Of course, there's no problem to have a uniform coupling or uniform coupling plus spatially random coupling, but at the moment they only have a spatially random coupling, so G is 0, because that helps their equilibration. So they're doing very large systems, again using fancy GPUs and new algorithms and so on. And so I don't want to, this is an advertisement, the paper should be out, and I'm not part of it. Okay. But I'll just mention one result that Avishkar allowed me to show you. This is now a full calculation of this model. You're doing quantum Monte Carlo, and you measure in any given sample the boson zero frequency correlation function as a function of position. Then you take that function and you just look at its eigenfunction. Think of it as a matrix and diagonalize it. And from that, you get a localization length. And so this is essentially an exact analysis of this theory. Nothing's left out other than the uniform coupling is 0. And what you see is exactly what we saw in the large M self-consistent Hartree analysis. At higher energies, extended states in this non-monotonic increase, which we think is a very good signal of the appearance of these localized bosonic modes. Okay, so what I think would be great in the future is for experiments somehow to see these localized modes. And we have helpfully given a few pictures here of what they might look like. All right. Okay, so that's so there's also some short noise. So this is work by Alex Nikolenko. He's not here yet. My student, he'll be here a bit later. So this was motivated by some very nice experiments at Rice by Doug Nadelson, where they see short noise in the Fano factor in the strange metal around 1/3, which is quite different than what you expect in a clean metal. And so Alex and Avishkar have this analysis in this model with G prime and V not equal to 0. And they do find, although the work is still in progress, a regime that's similar to the experiments. But this, again, I think there's a lot more to be understood here. And also, it'd be great to have more experiments on short noise and other materials. Strong nonlinear response. So this is the work of Sergey over there. He put it on the archive yesterday, so I think it's going to appear tonight. So again, you take the model with G prime and V and look at nonlinear response. So using Keldysh methods. And so they have general results for the third order conductivity and also to all orders in the electric field. But the main point is that the response in this strange metal is actually is enhanced by a factor of 1 over temperature in comparison to a Fermi liquid. And this is because of the non-analytic dependence of the energy, self-energy. So when the self-energy is analytic, like in cos omega squared in a Fermi liquid, that gives you a much weaker response. But with the log omega dependence of the self-energy in a marginal Fermi liquid, you get a it really has a dramatic enhancement in the nonlinear physics. So finally, it seems like here's a prediction. So the theory, well, also the localized modes, you could say, are a prediction of this theory. So there's also work on now magnetic field and cyclotron resonance, which is being studied by Peter Armitage. So motivated by these experiments, How You Go, who's now at Cornell, showed that there's a Cohn's theorem says that the cyclotron frequency shouldn't have any singular response from long wavelength effects. And that's true in the clean model. But once you go to the random Yukawa model, you do get significant correction to the cyclotron mass that were computed here. So this is work in progress with Jorg's group on one of the other big open problems that's been around, which is this famous t-squared cotangent of the Hall angle in the cuprates. So we're studying that, and it's clear that that requires even greater degree of disorder to have any hope of understanding the data. But let's see, that's work in progress. And finally, we've also been looking with Ilya and my student Chenyuan Lee on superconductivity, what happens to this theory as it goes superconducting, which it does. You can compute TC and the spectral function below TC, this fluid density, and so far. So this hopefully should be out soon. And there's a correlation between TC and this linear T-slope of the resistivity. Okay, I think that's all I have to say. Thank you very much.
Subir, very nice talk. I'm not questioning any of your calculations. I can't. It's sort of
Please do.
great. But your talk, like many others in the theory community, are strongly motivated by the phenomenological properties of the cuprates, right?
Yes.
All right. So as an experimentalist, I would like to convey some insight or maybe concerns also. So first of all, and you in the overdope part of the phase diagram, you have a Fermi liquid, right? And perhaps we can agree on that. You have a large Fermi surface as predicted by band theory. You have quantum oscillations consistent with the Fermi surface seen by photon emission.
All right. Yeah.
Right.
All right.
And so one experimental fact is that deep in the pseudogap state, in good measurements on good samples, you again have T squared.
Okay, I have not talked about the pseudogap at all.
I understand that. I'm just giving a.
I've only been talking to the right-hand side.
I will come to that. Just give me a minute.
And but I should say to be, our theory of the higher temperature pseudo. Let me just put this up, if you don't mind.
Yeah.
The theory of the higher temperature pseudogap. This is the only place where I mentioned the pseudogap, this spin liquid here. But this is
give me
at higher temperatures. Yes.
So you mentioned the cotangent of the Hall angle, this dichotomy that goes back to the late 80s.
Yes.
Let me just give you just a moment. Okay, so if you look at the cotangent of the Hall angle, it is T squared where you expect it to be T squared on the highly overdoped side and deep in the pseudogap state where the resistivity is also T squared. But it continues to be T squared through the pseudogap into the strange metal regime, unchanged. So in other words, the prefactor of this T squared of the Hall angle is the same across doping and across dupe rates, and it's the same. It's T squared up to 400 Kelvin.
Yeah.
So if you interpret the T squared behavior on the overdoped side as a T squared scattering rate, you're forced to conclude that this T squared scattering rate is alive and well throughout the strange metal region. How can you reconcile that? So people like
I'm not forced, but you may be. I'm not forced to conclude that, but anyway, okay.
So people like Horst Schirmer in the late 80s already put forward the idea, which is sort of gotten forgotten, that you have essentially a two-component system. You have the dope carries, and then you have some activated charge. So in other words, the carry density acquires temperature defects.
Yeah, okay. I mean, I would say that's not been forgotten, but it's been ignored for good reason. I mean, that's not a reasonable model of anything. Come on.
Can you get the T squared Hall angle?
Okay, I will say, let me not anticipate. That's in process. So let's just let Davide and Avishkar finish their work. We're working very hard on it right now. And in a few months, we hope to have something to say. Let me just say, but we are optimistic. There is a paper by Avishkar from about 5 years ago, where in a simpler model with significant inhomogeneity, he could get that behavior. But what there is one point of view made that I will agree with. Even in the linear T resistivity, for example, there's so-called bad metal regime at high temperatures that maybe you see in cold atoms. And then there's the low temperature strange metal regime here. There's no change in the slope, whereas the underlying physics that we would write down for these two regions is very, very different. And I agree that that's a major open problem. We don't understand why the slope doesn't change through very different regimes.
Surely at high temperature, you consider photons.
Next question. Okay, go ahead.
Subir, so suppose you have this localized bosonic mode.
Yes.
Intermediate energy. Now, can you provide some intuition how they react back to electrons, why we should care about them?
Well, that's sort of what we compute. There's a coupling G prime, and the reason they're localized is precisely because of the damping. If you didn't have the Landau damping, the localization is not as strong.
Suppose they're local, I mean, they're local, they exist. So, but why they contribute to
Well, I mean, that's
observable electronic effects?
well, so this is an actual calculation of the electronic self-energy, and there's a similar in the quantum Monte Carlo, and this whole, at least this low region. I mean, okay, this is applicable everywhere in the sample, even at higher energies. But this extended region here is coming from the localized, very small energies down here. Okay, I don't have a, I think you just look at these pictures. This is how things evolve as a function of energy scale. They're extended states, then all these localized, I'm just showing one of them, it's quite a few of them. This is just the wave function of one of them. And then they start to get more extended as you go to the point D.
Okay, thank you.
Yeah, so again on these localized modes, so I wonder whether what happens to the entropy or heat capacity as a function of temperature in the presence of these modes within the theory, and what is known from experiment. I don't know the answer to either question.
Well, I don't know. No one that's seen these localized modes. I mean, maybe one could reinterpret some of the STM data to see if they're there.
The overdope side.
Yeah, for example, I mean, you'd have to do some kind of Macmillan type analysis of the STM data to see if there's you get some electron localized boson scattering, for example. It's possible, but no, I mean, specific heat, you know better than me. I mean, it's T log T, and at least that's what Ty Fair claims. So yeah, I don't have the data here. We have computed the density of the bosonic modes, and it's constant down to low energy. So it's T log T, and maybe it gets slightly more singular numerically at very low temperatures.
So T log T is it's at one doping.
Okay, I see.
The foot region, I don't know what the data.
Yeah, I don't know. Okay, I think there may be the electron dope. There may be some data. I should look into that. That's a good point. I mean, yeah, here I suspect they have some measurements down here. Yeah.
Yeah.
Could I ask you a simple question about this nonlinear transport result that you are?
You should ask Sergey. Where is Sergey?
Whatever, right? So that effect that you mentioned, is it really distinguishable from heating, from simple Joule heating?
Yes.
It seems like if you just take your linear in T resistance, trade T for electric field dependent T with all these inelastic rates, which are 1/T here, right? And it'll be way more singular than 1/T that comes from non-elasticity of self-energies or whatever.
Okay, Sergey can answer.
Yeah, so this effect is present both in Joule heating and in response that doesn't excite the energy density. So it's like overall term on top of the Joule heating, for example, too.
I mean, you can couple the system to phonons and let them relax the heat to the phonons, for example. But there's still an effect, and that's all discussed in this paper, which you can read tonight.
Okay.
So there will be additional divergence from the energy relaxation rate that should go to zero as temperature goes to zero, and we don't really know what it is. incorporates, but this TF over T factor is on top of that.
Okay. Subir, I was just curious, did you guys consider, and I mean, just seeing the computational power you guys are having, just the case of the random field disorder where you couple linearly to the
No, not in these days. I mean, there's one paper I wrote with Sean Hartnell and Raghu Mahajan where we just did perturbative analysis and found really strong effects. So I'm assuming there's no random field.
Do you think it's going to be very different if we do that, or?
I probably yes, I would say yes.
Are these localized modes fundamentally different from polarons?
Polarons. I mean, polarons come from strong coupling, say, between electrons and phonons or something like that, or electrons and magnons. Here, it's really much more of what we're saying is that at any coupling, at very low energies, because of the renormalization. So, that's the physics of this transverse Ising model. Yeah. It's more like the random singlet phase of the transverse Ising model, if you know something about that. So what happens is that by accident, you get some regions that are very strongly coupled because they have very negative mass. But there's just a few of them. But then, when you start, you think you can get rid of them, but then they generate other couplings, and eventually you get this phase with lots of localized modes with who's. Huh? It's not self-trapping. I mean, eventually the modes are actually, this localization length is ultimately going to infinity at zero energy, but very, very slowly. They're becoming extended again. That's the physics here. Yeah, so it's really very much like the transverse Ising model as far as we can see.
One more question that might.
Maybe one more comment. So one remarkable thing with this connection, and this is understood already by Thomas Boyta, if you don't mind. Why is there this connection? So on one side, you have an insulator, and you have a discrete order parameter. So on this side, you have a continuous order parameter and a metal. And basically, roughly the effect is that having a continuous order parameter enhances the fluctuations, whereas having a metal damps them. And somehow these two effects exactly cancel with each other to make this mapping possible. And it's ultimately related to the fact that if you take a 1D XY model with 1/tau squared interactions, it has the same behavior at low temperatures as the 1D Ising model with short range interactions.
What determines the energy scale at which the bosons start delocalizing again?
Yeah, at this point, I don't think we understand that. It depends on the numbers, I'm sure. Yeah. Avishkar may be able to say better. Yeah.
Let me ask the last question.
Yeah.
This is about coming back to the very beginning of your talk. So you started with materials and a critical point and some evolution of the firm surface. Normally we take boson in this case, having momentum dependence, and picked, the susceptibility is picked on the particular momentum equal to zero.
Right.
Later in the presentation, we
Yeah.
eliminated momentum dependence of the boson. Nevertheless, the boson is almost critical. Does it mean that the transition is towards this infinity of states with arbitrary value of Q?
Okay, so when you're considering this critical point without disorder, or the spin density wave point without disorder, they look very, very different. Okay, but once you put in the random coupling, once G prime becomes random, once you add the G prime term and it's random, if there's some e to the I k dot r factor here, it doesn't make much of a difference.
Right.
So in the random case, oh, yeah, that's yeah. So if this was for this data, yes, you're right. We haven't put any pi in here. But if this was, you're plotting the spin density, you would take this plot and put a pi multiplied by pi basically. It also applies in that case. So that's the universality that we're claiming, that Once you add in disorder, then the Q equals 0 and finite Q critical points are the same.
But for example, when you write self-consistent equations, you
Yeah,
have to put some momentum dependence of the boson and then integrate over it. That will change, of course, powers, etc.
well, again, not when you compute the self energy, the electrons, you probably have to put it in, but again,
Like this formula.
yeah, but because you're doing a G prime squared at this order, they just cancel out.
Thanks very much. Okay, great. Where is that? Second talk, Berg, Weizmann, new generation of two-dimensional quantum liquids. Well, it's preparing, I forgot to say important word. So this workshop actually became possible because of grants that we got from Simons that allowed us to run more workshops than we usually do. So from all of us, thanks to Simons. It is. Sorry.
Okay, so we start by thanking the organizers and the Simons Foundation for this wonderful pre-March meeting. It's a real pleasure to be here as always. Yeah, I'm going to talk about novel 2D electron gases. I've been fortunate to work with many wonderful collaborators on this work. The work that I'll be presenting was done with Vladimir, who was a student at Stanford, Steve Kivelson, Agnes Valentin, who used to be a PhD student at ETH Zurich and now has moved to a postdoc position at the Flatiron Institute. And she was working with Sebastian Huber from ETH. And these are some of the papers, some of the work I'll present is not yet posted, hopefully soon. So as you all know, the homogeneous 2D electron gas is sort of a cornerstone of correlated electron physics. It's of importance both from the fundamental point of view and also from the practical point of view. It's kind of the basis for LDA, for example. And it's characterized by this one-dimensionless number, Rs, which is basically the ratio between the average potential energy and average kinetic energy per electron. And of course, we're particularly interested in this problem when Rs is either order 1 or even bigger than 1. This is an extremely difficult problem because this is exactly the regime where we don't have any small control parameter. Nevertheless, there's been a lot of hard work on this model, so we know quite a lot about its behavior. And it turns out that it's most probably has a very simple phase diagram, actually, okay, known from variational Monte Carlo calculations. From all the way from small Rs, weak interactions, to the strongly interacting regime, there's a homogeneous, basically Fermi fluid, Fermi liquid. And then somewhere around Rs equals 30 to 40, there's a transition to a Wigner crystal. The Wigner crystal can be either a spin antiferromagnetic or ferromagnetic, depending on Rs.
What is on vertical axis?
Yeah, it's some weird measure of the energy that these guys plotted. Think about it as just energy per electron. Okay. All right, so this is very simple. Okay, as simple as it gets, just electrons with the parabolic dispersion interacting via long-range Coulomb interactions. Okay, but over the last several years, maybe especially 5 years, there's been a lot of developments in designing new types of 2D electron gases with new features. basically you can think about them as sort of generalizations of this old classic problem, either different dispersions, more flavors, or both, Berg curvature, and so on. I'll show a few examples. And we can tune these systems. There's a lot of tunability, both in terms of the band structure, the electron density is gate tunable. Some of these systems are extremely clean, and they're much richer. They have much richer features, and therefore they also show much richer physics. Okay, and that brings new opportunities, but also new challenges. How do we tackle this complexity? The simple homogeneous electron gas was sort of hard enough. How do we tackle this new complexity that we're faced with? And the strategy I'd like to propose is to build in this complexity sort of step by step. Most of the talk I'll be presenting a simple test case, namely a two-valley 2D electron gas with anisotropic dispersion. Okay, so it's kind of one step beyond the homogeneous electron gas, and I'll show that already here there's some interesting physics. And this is actually realized in aluminum arsenide to the electron gases in experiments done in Princeton and Shagan's group. Okay, so a novel correlated to the electron gases. Okay, so you've all seen twisted bilayer as well as twisted n-layer graphene, crystalline multi-layer graphene systems, and multi-layer transition metal chalcogenide systems. So these systems have new features compared to the electron gas. Okay, so these are multi-valley systems. The dispersion is very anisotropic. It's not just a parabolic dispersion. Some of these systems have a Moiré superstructure. They have a non-trivial Berg curvature and so on. Okay, and this really leads to a dazzling variety of new phenomena. Okay, so both spin or in valley generalized ferromagnets and other types, mud insulators, superconductivity, and most recently also both integer and fractional Chern insulators and so on. Okay, so for example, one system that I'll just want to present briefly, which I'm particularly fond of, is this crystalline rhombohedral graphene. Okay, so the reason the system I think about is just a complicated homogeneous electron gas. There's no Moiré lattice. All the richness is coming from the band structure, basically, of this system. So these are stacks, or either 2 or 3 or more layers of graphene. There's no twist angle between them. The different graphene sheets are actually aligned with each other. Okay, but the band structure is of each valley. This is when it's doped with holes, is strongly trigonally warped. Okay, so the top of the dispersion has these 3 pockets, and then there's a regime where there are actually 2 Fermi surfaces that are sort of concentric warped circles, and then it becomes just a single Fermi surface at each valley. Okay, and this leads to this very rich and complicated phase diagram as a function of electron or hole density and displacement field. These are experiments done in Andrea Young's group. Okay, you see this is measurement of the inverse compressibility. You see these very sharp jumps in the chemical potential, which are basically transitions between different phases with different patterns or broken spin or valley or both degeneracy. Okay, so this phase diagram has been mapped in great detail using quantum oscillations. We know pretty well what these different phases are. Okay, what the number of the degenerate Fermi surfaces are and what their degeneracy is. So just from the dependence of the Shubnikov de Haas oscillations on a density and displacement field and magnetic field, okay, we know that it in these different, and also bilayer graphene experiments done in Andrea Young and also Stefan Najperger's group. Okay, so this is now transport resistance, and on the phase diagram you see that it's quite common to see between, right at the border between two ordered phases, right at the verge of a phase transition, there's a sliver where the system becomes superconducting. Okay? And the nature of this superconductor is not quite understood yet, but there's some things that are known about it. Okay, so somewhat very surprisingly in bilayer graphene on BN, for instance, the superconductivity is not there, zero magnetic field, but it actually appears in the presence of an in-plane magnetic field. It sort of turns on. That's one of the puzzles in the system. Okay, TC can vary depending on the system and the substrate in this range. There are both singlet and triplet superconductors observed. And as I mentioned, superconductivity often appears right at the border of some phase transition. Okay, so how do we deal with all this complexity? Okay, so clearly understanding all this physics, which is all occurring in the regime where RS is maybe between 5 and 15, is obviously very challenging. What I'd like to do is to sort of strip this system apart a little bit to unravel this complexity. I'll consider a much simpler system. Okay, 2D electron gas with two valleys. Okay, I'll retain that feature. C4 symmetry instead of C3. Okay, so I'll have just two Fermi surfaces of the two valleys that live on the X and Y points of a square Brillouin zone. Okay, and by symmetry, each Fermi surface is allowed to be distorted into an ellipse, but the two Fermi surfaces in the X and Y points are related by 90-degree rotational symmetry. Okay, and so this situation is realized in aluminum arsenide quantum wells that were pioneered by Shagan's group. Okay, these are extremely clean to the electron gases, not quite at the gallium arsenide level, but still very clean. And moreover, the effective mass, the average effective mass between the two directions is much higher than in gallium arsenide. Okay, which actually makes it easier to access the strongly correlated regime at higher electron densities, which means that disorder levels are expected to be lower, and we can observe some of this correlated physics. Moreover, eta, which is the ratio between the effective masses in the two directions, okay, mx over my, is quite large. It's 5. Okay, so these Fermi surfaces are very, very elongated in one direction. Okay, and what does the system do that the simple 2D electron gas does not do? Okay, so it turns out that it has a very interesting behavior. Okay, so this is an experiment done in Shagan's group, and what they observe as a function of density, this is the resistance in the two crystalline directions. Okay, either 100 or 010, and you see that at high density, the two resistivities are the same, but there's some critical resistance where they become different. Okay, and this difference can be actually trained by applying strain. Oops. Okay, so the interpretation of this experiment is simply that the system is spontaneously choosing a valley. Okay, so this is valley polarization. The system, all the electrons choose whether to go to the X or Y valleys. Now, in terms of RS, this transition actually occurs somewhere around RS equals 20. Okay, and the system ultimately undergoes a metal to insulator transition, but that's at yet lower temperatures, lower densities when RS is close to 30. Okay, so ultimately, probably the system is becoming some kind of regular crystal. There's even signatures of spin polarization as well in this low density regime, but not here. Here it's looks like the system is valley polarizing, but not spin polarizing. Okay, so I'd like to understand how this behavior emerges out of this band structure with two valleys, which have a very strongly anisotropic dispersion. Okay, so what we'd like to understand is the phase diagram of this type of 2D electron gas. And there are basically now two parameters instead of one. In the usual 2D electron gas, there's only a single parameter RS or density. Now there's an extra parameter, which is this anisotropy of the effective mass. And as theorists, we want to add another axis, which is imagine that the Coulomb interactions are screened by metallic gates, and d is the distance to the nearby gates. So that tunes us between basically long-range interactions when d is larger than the distance between electrons, and short range interactions. Okay, so that's going to be a useful tuning knob. Okay, and we can expand around various limits to try to understand physics. So we can do a weak coupling expansion at small RS. We can do a strong coupling expansion. And it would be useful to also go to the limit of very small d when the effective Coulomb interactions are very strongly screened. So then the interactions are short ranged, and we can ask what happens when the electrons are dilute. So basically when the distance between electrons is much larger than the distance to the gate. So we have effectively contact interaction. Okay, but ultimately the real system lives in here in the most difficult regime, RS intermediate, and D is small in some value, some given value of eta, that 5.2. Okay, and here we'll have to resort to numerics. We'll do variational Monte Carlo calculations. Okay, so this is the Hamiltonian, very simple. We just have an anisotropic effective mass where the sign of the anisotropy is opposite for the two valleys. And we have long-range Coulomb interactions. Now, because of the fact that the density of electrons is very small per unit cell, this drawing is not to scale. These pockets should really be tiny compared to the size of the Brillouin zone. We're going to neglect inter-pocket or inter-valley scattering. Okay, that's because the Coulomb interaction for large momentum scattering is much smaller than the interaction for small momentum scattering. So basically, we're only allow electrons to scatter within each one of the two valleys. That's the approximation we're making. But other than that, the interaction doesn't depend on either spin or valley. The interaction between two electrons of different valleys is the same as the interaction between two electrons within the same valley. Okay, so these are our two parameters. Eta is the mass anisotropy. M star is the geometric average of the masses in the two directions. Okay, so some effects that we're neglecting: no electron phonon coupling, no spin orbit coupling, and no intervalley scattering. And these effects we believe are small, but we can negotiate later what their effects should be. Okay, so the first thing we can do is do a Hartree-Fock analysis. We don't expect that to work particularly well in the intermediate RS regime, but still there's some interesting lessons from doing that. So this is now the Hartree-Fock phase diagram of the system as a function of RS and anisotropy eta. And you see that what happens here is this, as you increase RS with a given value of anisotropy, you undergo this cascade of transitions from the symmetric Fermi liquid state to various partially polarized spin and valley states until you reach a fully polarized spin and valley state when RS is close to 2. Okay, so a couple of interesting things to note here. As one would expect, Hartree-Fock greatly also overestimates the stability of these symmetry broken phases. Okay, so basically breaking the symmetry is the only way for Hartree-Fock to lower the energy. Moreover, in the state where you choose 2 out of the 4 flavors, there's a degeneracy actually between the spin polarized state, where you occupy both valleys equally, but only with a single spin flavor, and the valley polarized state, where you choose one of the 2 valleys and occupy it with both spin up and spin down. Okay, within Hartree-Fock, there's no difference in energy between these 2 states. This is an accidental degeneracy. These 2 states are not related by any symmetry of the system. So we expect this is really an artifact of the Hartree-Fock method. When we go beyond Hartree-Fock, we expect this degeneracy to be lifted somehow. Okay, and finally, it's interesting to note, okay, so the eta here is the bare anisotropy. That's the parameter we put into the Hamiltonian for the different effective masses. The actual Hartree-Fock solution actually renormalizes this anisotropy, and it always renormalizes down. The interactions like a more isotropic Fermi surface. Yes.
This translation invariant Hartree-Fock.
Yes. Yes. Yeah.
But interaction is not local, right?
No. No.
So we have different interaction between pockets and within pockets.
No. So yeah. So the interaction is not local, but we neglect a large momentum scattering.
Then you have the degeneracy.
Then I have the degeneracy. By the way, if I include the large momentum scattering, which is expected to be small, that would actually favor the spin polarized phase and not the valley. So it lifts the degeneracy, but in the wrong way compared to experiment. Yeah. Any other questions? Okay. So let me first describe the variational Monte Carlo results, and then I'll try to understand them. Okay, so this is the method applied often to the homogeneous 2D electron gas. This is basically the source of our best knowledge about that problem. So what you do is you write a variational wave function, which has these components. You start from Slater determinant. You multiply it by a Jastrow factor that builds in correlation effects. And finally, there's a backflow transformation. Okay, so that's a technical name. What you actually do is you evaluate this wave function with the Slater determinant and the Jastrow factor, not at the coordinates of the electrons, but at r tilde, which is some function of the coordinates of the electrons. Basically, you move every electron by some amount, which depends on the nearby electrons. So this is why it's called the backflow. And one way to understand what this backflow transformation is doing, okay, if we just use this Jastrow Slater wave function, the nodal surfaces of this wave function are exactly the same as those of the Slater determinant, because we multiply it by a positive definite factor. What the backflow transformation allows us to do is also to move the nodal surfaces compared to those of the Slater determinant. Okay, so it builds in some extra freedom into our variational wave function. Okay, so this is the variational Monte Carlo wave function for this model, for this two-valley anisotropic model as a function of Rs and the mass anisotropy eta. Okay, so there are three phases that are seen here. The green is the symmetric Fermi liquid phase, no broken symmetry of any kind. Okay, the blue here is a fully polarized, fully valley polarized spin unpolarized state. Okay, so you see that this state, of course, is not favored when the anisotropy is equal to 1, but turning on the strong anisotropy strongly favors the state. In particular, if we're here, that's the value corresponding to aluminum arsenide, will cross into this phase around Rs equals 12. Okay, and then finally, if we increase Rs even further, we go into this yellow region, which is the spin and valley polarized phase. Okay, so some features here, they're very different from the Hartree-Fock. It looks like this variational wave function when you turn on the mass anisotropy strongly favors valley polarization. Okay, so yeah.
Sorry, when you say full valley polarized state, it's really full polarization. That
Yes.
says that one Fermi surface disappears.
Yes, yes, yeah. So we tried in our variational search, we tried partially polarized phases, and it turns out that it just likes to jump directly from the fully polarized one to the unpolarized one. Now, let me mention that a two-valley electron gas was studied using variational Monte Carlo without the mass anisotropy before. They found basically a transition to the Wigner crystal, which I'm not showing. We actually didn't search for the Wigner crystal, somewhere around 30, similar to the usual to the electron gas.
This jump to full polarization, is it the subject of the, is it only for parabolic band, or if you have a parabolic band, it will happen as well? Or?
I don't know. Yeah, I don't know. This is a parabolic, elliptical kind of Fermi surface, but
Right.
yeah, we
for pure parabolic space.
Yeah.
So the density of it's 2D, so density of it just constant.
yes, exactly. Yes.
All right. Yeah,
Yes.
which should be somewhat specific, right? So,
Yes, yeah. So right. Well, on the other hand, this is the effective mass approximation, right? So
right.
at low density, yeah, but it's definitely not true at higher energy.
Well, there is work also, right?
So you know, at low energy, this is the right symmetry of it. I mean, if you expand around the x and y points, these are the
it's
yeah.
leading.
Yes. Okay. Yes.
Erez, looking at your phase diagram, is there a place for a more exotic phase like Overhauser charge density wave, for example?
Right, yes. So yeah, so within our calculation, we didn't find sort of pronounced charge density wave correlations, and we think they should have been there. So the calculation imposes translational symmetry, but if the system wants to create the charge density wave, there should have been strong charge density wave correlations, and we didn't find that.
It's a limitation of
Just one second, guys. So this will be a question.
Okay, we'll yeah. All right, so yeah, so that's the result. So that's basically our main result. So the anisotropy of the Fermi surface actually strongly favors the formation of this fully valley polarized state. Okay, this is the
Early, right?
sorry.
It favors it very early. Oh, at 15. Okay, you changed the scale.
Yeah, yes, yeah, sorry. Yes,
see.
yes, yeah.
Scale changed.
Right.
Sorry.
Okay, the energy differences between the two different states are shown here. They're embarrassingly small, okay, as often happens in these types of calculations. Okay, so this is as a function of Rs for a fixed eta of around 5. And the energy of the symmetric state was subtracted here, so that's 0. You see the crossing. This is the fully valley polarized spin unpolarized state. This is the spin and valley polarized state. But the energy differences are sort of a few percent of millivolts per electron, very small energy differences. This is what happens as a function of eta for a fixed Rs. So when eta is equal to 1, as you might expect, the spin and valley polarized phases are degenerate. Okay, the system doesn't care whether it polarizes in spin or valley. But the moment you turn on eta, this anisotropy of the Fermi surface, these two states split, and the anisotropy strongly favors the valley polarized over the spin polarized phase. Okay, and this is what happens to the fermion occupation number in momentum space and k along the two directions in k space, x and y, for one of the valleys. So you see this. We actually treat this shape of the Fermi surface as a variational parameter. We optimize over it, and it gets renormalized. So there's just as in the Hartree-Fock calculation, the actual anisotropy of the Fermi surface is smaller than the bare anisotropy. But in the valley polarized phase, this renormalization is not so extreme. It's actually much bigger in the spin and valley polarized phase. Okay, so now how do we understand this effect? So why does the anisotropy of the Fermi surface favor the valley polarized phase? We can address this question from various limits where we can do controlled calculations. One limit is small rs. So at small rs, of course, the ground state is always going to be the symmetric Fermi liquid, but we can ask how does the anisotropy of the Fermi surface affect the susceptibility of the system towards different states, spin or valley polarized? And we can do this analysis within RPA. So it turns out that there is a very simple and generic result, okay, which you can already see at second order. This is basically correlation energy, and the result is that for any dispersion which is different in the two valleys, in particular anisotropic dispersions which have an opposite sign in the two valleys, the valley susceptibility is always bigger than the spin susceptibility. Okay, so both states, valley and spin polarized, are not the ground state, but the mass anisotropy always favors the valley compared to the spin. And this is a correlation effect. This is missed within Hartree-Fock. This is really an effect of electron-electron correlations. Okay, so that's one limit we can analyze. Another limit is the dilute limit, where we imagine that there are screening gates that are not there in the experiment, but let's put them in our theory. There are screening gates that are closer than the inter-electron spacing, and then we can treat our electron gas as dilute. Only 2 electrons collide at a time. Okay, and that limit, what we can do is basically solve the 2 electron problem exactly for arbitrary coupling. Okay, so this is just calculating the scattering matrix of 2 electrons, and then use that as our effective interaction, and treat that with many body methods. Okay, so this is well known for the homogeneous electron gas. What we find as we do that is that because of the different dispersions, there's a different scattering amplitude for two electrons in the same valley compared to two electrons in different valleys. Okay, so this is the scattering amplitude for two electrons in the same valley. V naught is the strength of the contact interaction. Okay, so that it just depends on the average effective mass m star, and it goes down logarithmically with energy. Here it's evaluated at mu, the chemical potential. W is the overall bandwidth. Okay, so this is as usual in 2D. The effective interaction is renormalized down logarithmically with energy. And it turns out that that's also true for the intervalley interaction. So if you have two electrons in different valleys, but because of their different dispersions, the renormalization of the interaction is much slower. It's actually suppressed by this factor of 2 over eta plus 1 over eta. Okay, so in the limit of, first of all, the intervalley interaction is always stronger than intravalley interaction. That favors valley polarization. And we can take this limit, okay, if the anisotropy is very large, the system would actually valley polarize. Okay, so at the end of the day, there's a very simple sort of intuitive 10. Oh, okay, yeah, I'm pretty much done. Yeah. So just a couple of slides. So at the end of the day, there's a very simple sort of intuitive explanation why valley polarization is favored by this anisotropic dispersion. Okay, so if you think about the electrons in the two valleys, interactions tries to localize these electrons to try to allow them to avoid each other. But if you're an electron in this valley, you can very easily localize in the x direction where the mass is large, but it's much harder to localize in the perpendicular direction, and vice versa for an electron in this orange valley. Okay, so if the system is not valley polarized, this is now real space. Okay, so it's hard to localize these electrons in such a way that they would avoid each other effectively. But if you valley polarize, you can fit all the electrons together much better. Okay, so this is an analogous phenomenon the phenomenon that happens in nature. Okay. Yeah. So finally, let me just say a word about very large RS. Okay, so there's one more limit where we know how to analyze the problem. That's large RS, and that limit the system would just crystallize. The system forms a Wigner crystal, but it turns out that the valley degree of freedom still has some interesting effects. So okay, if you expand the energy of the system per electron in the large RS limit, the lowest order term is just 1 over RS. That's the Coulomb interaction. That would just favor a triangular Wigner crystal as usual. But the 0-point motion of the electrons around the equilibrium position that gives rise to this 1 over RS to the 3/2 term, that actually knows about the valley polarization. Okay, so the phonon dispersion, if you like, of the Wigner crystal depends on the anisotropy of the dispersion, and that mediates long-range valley interactions. Okay, so this effect is not there in the usual homogeneous electron gas, where there are only spins. And spin exchange interactions are exponentially small, so they're much smaller than these terms. Okay, so you can minimize the second term that depends on the 0-point motion of the Wigner crystal phonons over the valley configuration of the Wigner crystal, and it turns out that that actually favors this sort of pattern. It's not what we hoped for, but this is what comes out. Okay, it's anisotropic. It breaks the C6 symmetry of the triangular Wigner crystal, but it's not valley polarized. You actually have a column with one valley and a row with one valley and the next row with the other valley and so on. Okay, so yeah, I'm basically done. And yeah, thank you very much.
So let me point out an issue with these experiments by Mansour. So in this very low density limit, that they think that they are getting the spin polarized state.
Yes.
We looked at those numbers carefully, and I think there is an issue because they have 300 Kelvin temperature. And when you compute J, it's of the order of 10 millikelvin. So they would be at a temperature that is much higher than so they might be in the Wigner crystal, but the spin is quite thermally disordered. So maybe the question is there a way?
I see. Yeah. So you say this value, this value is much bigger than the spin exchange.
Yeah, so the temperature is 300 millikelvin, and the J we estimated like with very naively just using isotropic mass.
Yes.
It's about 10 millikelvin.
I see.
It would be, so maybe the question is, have you looked at what is the J for this?
Yeah, we actually haven't done any simulations in the Wheeler crystal yet. Okay, so we can probably estimate the J for you in the spin polarized phase, but that's probably not the same. Okay, so yeah, I don't know.
Yeah, Wigner crystal, don't you get a long range spin model, quantum spin model of the Valley spin? Pseudo spin?
Yes.
So
Yeah.
we haven't looked at that yet. Or?
What we say is the following. So it's basically a classical model. So
Why was it not quantum?
yeah, so there's sort of a transverse field. You can tunnel between the two valleys, but that's at the higher order in 1/Rs.
You don't get any transverse exchange.
No, so that's exponential in the
I see. That's also.
yes.
Whereas, could I provide another argument for why valley polarization, which seems to be distinct from what you said, and you'll say why it's wrong. So can I forget about spin for a second, real spin?
Yes.
Then the valley is just a pseudospin.
Yes.
And what you're describing is pseudospin ferromagnet.
Yes.
Right?
Yeah.
So if the valleys were identical,
Yes.
then it would have been an SU2 ferromagnet.
Yes.
Right? But now that they are, not circular.
Yeah.
It's an Ising ferromagnet, right?
Yes.
And what provides this Isingness is the distinguishability of the orbitals, right? It's the exchange in one valley is larger than in different valleys.
Yes.
So it's either up or down. Why do you need to do this fish thing?
Yeah.
Any valley polarization is Ising orbital. Any valley polarization is Ising orbital.
No, but I think
SU2, that's because orbitals are distinguishable, right?
Yeah.
So there is not as much exchange between them as in the same valley. So it'll polarize in the valley.
No, okay. So I mean, let me make sure I understand what you mean. So I mean, you're not thinking about the fluctuations, the fact that one is an Ising order parameter, the other one is
No.
So the exchange energy is the same. You don't get any more exchange energy from the fact that it's
so
discrete.
if I put all electrons in the same state, which is a superposition of one valley and the other,
Yes.
right? So will the energy depend on the angle, so to speak, rotation angle?
Yes, but not because of exchange. The exchange energy would be exactly the same.
Exactly the same.
Yeah. So just to finish whenever all the electrons are in the same orbital, and it doesn't matter if it's one valley or the other valley or some superposition, the exchange energy doesn't care. You gain the same amount of exchange energy. We can discuss it. Yeah.
Discussion.
Yeah.
Raphael and then Boris and go ahead.
So you also show that there are other systems that have hexagonal symmetry, and then you have three valleys.
Yes.
I mean, shouldn't this case have some frustration or something that makes this little different, or I don't know, have you thought about it? Or...
Yeah. So right. So I mean, the systems I mostly showed have they have a threefold symmetry, but there are only two valleys. The valleys are in the K and K prime points. But if you had a valley in the M point, that's an interesting system. We studied it in the context of the Wigner crystal, and you get interesting sort of valley patterns, but not in the metallic phase.
Can you show experimental data when two curves split? Yeah, so I have a comment helping I think speaker. See these two curves, they split, and if you if you measure difference between resistivity, it's 5 times. I did, and 5 times means that this is a ratio of mass.
The masses, yeah.
And the ratio of mass is because ratio of ellipsoid axis is in square root of mass, but then conductivity takes square of
1/m. Yeah,
and that's exactly what is in this thinking, and tells that this is related to mass and acid. There's exact agreement.
Yeah, actually, maybe it's continuation of Jim's question. Did you look at the collective excitation setting? So if you have you can calculate chi, the question is that near the transition, was it diffusive or is it propagating or
So collective kind of valley.
kind of thermal liquid?
Yes,
Well,
yeah,
it's not
any
zero
kind
drama,
of collective
whatever,
mode.
whatever.
Yeah, no, we haven't. This is yeah, yes. I would think so, but yeah, but we haven't. Yeah.
Okay, tangential, but on the kind of vanilla to the electron gas, so superconductivity has not been observed.
Yes, yeah.
Fantasies that it
Yeah.
might be.
Yeah.
But in these new ones, it is.
Yes.
Do your calculations, you think, offer any insight into why these ones eventually go?
Yeah, so for me, one of the goals of this whole exercise is to ultimately develop a way to try to address that question. If we try to do the naive thing, sort of use the RPA screen interaction and see what kind of superconductivity it gives, it definitely gives superconductivity. The numbers are kind of small. It's a 1 millikelvin for these parameters, sort of right before the transition to the valley polarized phase. Yeah, so it's the usual. The interaction is repulsive, but if you look at the screen interaction, it's going to be attractive for a non-S wave.
Non-S wave.
Yeah, it's sort of a P wave within each valley. Yeah.
Okay. In the intention of asking last question, let me ask quickly. Maybe the same question that Yasha wanted to ask. When you showed us sensitivity, you were talking about the different susceptibility in different levels.
Yeah.
The orders you are telling us about are Q equal to 0 orders.
Yes.
Right.
Yes.
So when you try to do standard fermiology to deal with this instabilities, you deal with polarization bubbles at 0 momentum transfer.
Yes.
Right.
Yes.
When you talk about difference in susceptibilities, I thought you were talking about susceptibilities involving fermions from different vectors, which would be correspond to. Okay, maybe that question.
Yeah.
The same question.
Yeah. So
what about intervalley coherence?
Yeah.
Instabilities and finite momentum between vectors.
Yeah. So it's a good question. That in this small RS limit, this is not as favored as either spin or valley.
You say tau and tau, or tau and tau.
Tau and tau. Yeah, but you can also make tau and tau bar, and so that's another susceptibility. Yeah, so it's in small RS, it's always lower than either of these, but for intermediate RS, who knows?
Okay, wonderful. Thanks very much. Thank you. Time to come back.
Plug in the plug in
mechanics.
Hungry functions like
Yeah, but what is your experiment? Yeah, I mean, it is many people have found this for but most of that No, the spin liquid is in the background, even though this is in the metal, it's in the background.
Yeah.
So the creative bottom critical.
Yes, those are like.
Disorder, you explained it?
Yes, absolutely. That's
So
not
without
it.
disorder, so it's not coming from non-primary.
It is a disorder, non-permitted, but
Pure non-primary.
pure from liquid has perfect conductivity. It's a perfect set. Does not have passive conductivity. So there's a whole series of papers which have now shown this in different ways.
So let's say I don't include disorder, yes, but
I think we have one more.
Yeah, you have a non-fully liquid. If you look at electron spectral function, they'll be broad and like but if you measure conductivity, it will be fully liquid.
They're going to do something, conduct battery.
what is the definition of non-primary?
Yeah.
It depends on what you want.
Disorder free non-primary liquid there, like.
The electron spectral function,
Only that.
only the spectral function, not in transport.
Not in transport.
Yeah, that's a very important point. If you want to get non-Fermi liquid behavior in transport,
See,
we claim it only when it's transport, otherwise.
is there an easy way to understand?
Yes, it's well, it's essentially Cohn's theorem.
So, yeah.
Suppose I have a Galilean invariant system.
So K squared everywhere.
Suppose I have K squared. And I have very strong. Yes, then I can certainly in that theory get a non-Fermi but that theory still has a delta function.
Even in like a macroscopic sample.
Because of Galilean invariance. All right. Now the point is you take your favorite lattice system and take its low energy limit for its non-Fermi liquid.
Yeah, so it's kind of.
When you do that, you'll get some low energy theory. And my claim is that the low energy theory of the lattice system is the same as the low energy theory of Galilean. You had a quadratic component like Galilean system. Same field theory describing the low energy. All the singular corrections. This must mean that the singular corrections of energy must cancel out from vortex corrections when you do transport.
Okay.
So we have a paper, we've shown this explicitly in great detail. And you can actually do the calculation. But here's a quick, simple way to understand it. The fact that, in other words, you have some low energy theory that gives you quantum predictive behavior. That low energy theory has an ultraviolet completion with infinite conductivity. And that basically means that any conductivity, any resistivity you get in the theory must come from corrections to scale. But corrections to scale, they don't give you, are not responsible for the non-resistivity. So in fact, you end up getting a T squared resistivity. Yeah, you are, oh, okay.
You may know
Yeah,
my brother.
Yes, right. So you're here.
I work with Andre.
Okay, great.
But I work on I don't know, Mr.
I mean, Andre knows all this. Andre, at least they did it for the office.
But actually, I don't work on non-primary, but I work on, I don't use superconductors, superconductivity.
Yeah, that's, I mean, I didn't go into that. I mean, last year when I was giving this talk, I spent half the talk on balance point. Now I don't go, not this talk, but I wanted to just talk about the new results of the disorders.
Also, I have another question. So you show that food picture.
Yeah.
Now I see that at very high temperature, you again have that n is equal to 1.
Yeah.
So
Not
why,
very high.
let's say 200 Kelvin something.
Yeah, that's not that high. I mean, people go up to 600. So basically, the idea, there's a fan and then there's a food. The fan is coming from the extended state. The food is coming from the localized state. That's all.
But why do you again see that at very, okay, not high, but 200.
Yeah.
So n is equal to 1 here, then I see that
Yeah.
the exponent increases and then it goes to 1, right? In the temperature direction. Right?
I don't think we understand all that.
I see.
There's a lot more we understand. We understood different limits. Yeah, how to put the limits together in some coherent theory. Yeah, that's open problem.
Thank you. Sure, sure.
Okay.
I'll ask you something, but.
Yeah, sure.
What about the actual value? What about it? I guess. Let me find two P and probably the filter of the being also the strong evidence of the ITS Marie. And that means it's an interesting story. It's okay. But it's a question like whether it's short in the Marie skill. So I think here's the thing. Remember, like when during that time, I really upset of this linear T things. They talk to Dima, with TDJ linear T. I think Dima's claim like the gate modules, so we are in these graphene regions. We are calculating in graphene regions for dependency and individual utilities. Like in this graphene sample, there isn't a lot of disorder. Yeah, exactly. It's the same, like angle disorder and all this will be having on the Marie skill instead of the graphene sample. So in the Marie skill, what happened? You didn't see anything. It's something interesting. I mean, at that time, I really want to do some calculation of this disorder, angle disorder, whatever, to see what happened. Very interesting.
Okay, fantastic. I don't somewhere. And put this thing. No, I'm just working my stuff here. And so let's go to this. So this is what the problem I see. What you calculate is small. It's my point. Let's see. 7. You actually write it and simply. So I can write you is that which is this. This can be written as more than this. You see the background. What others? Translation. It says only nowadays smaller than. The next level. So this is small. So your length will be smaller than what? So, let's see. I just think.
Yeah, okay, so because it's actually decided.
Yes,
That's what I'm saying.
that's what I'm saying.
Yeah, no, I agree, I agree. It's not
So
small,
that's-
but
No, it's not. It's not the electric.
no, it's not that, it's a capacitance which relates to the.
Well, if it is for the model, I just don't know whether it's worth. Yeah, it's 6 months.
Now, your picture, you have one electrode, now the electrode. What is this electrode? What is this a cube or is it two dimensional? You're talking about quantum multiplier, that's two dimensional. Then this is just a number. And then I connect the line. So you know this, the calculate capacities of then you see big thing, okay, big thing. I'm slow. Let's say it's then it's over L over B, and look at like it's not this is bigger than one. So I need again look. So the capacity is really close, is L into G.
The cover of.
Something which is AP, and AP is enormously smaller than. That's not that capacitance which you do. Small city. It's not talking. Which is not. You're talking about only about these capacities. You say this like I'm saying it's not measured. Because in truth, you have to add it to it.
Actually.
So this is now. It can be multiplied by length. Then can be added by length.
Remember you said it's kind of.
This is length.
For a measurement.
No.
See,
Okay. What's his name?
People can still it.
It's length. That's gonna be multiplied by length.
So it analytically is
Which we measure in this setup is I ignore the range. Last year's to see is the range will be small compared to
exactly.
so it can't be measured because nobody knows X. So X
It's kind of like a story about
that's my I'm so I'm thinking the point of view of experiment. I'm so excited.
No, you don't have like some simulator that can help
Think
you
about
ignore
this.
some dimensions or whatever.
So
What is that?
All results Very compared to L. And this has microscopic size, has different size. So,
Well, I mean, you can they solve it numerically, why you care how to solve it as Or do you like the machine is smarter than you?
still when people measure something.
Yeah, I know. Or they solve it. Like they cannot solve it.
I know everything because this is your result. I am saying 18 is very small compared to them. That's why.
That's one kind of people like you cannot solve it and eventually like
It's so small.
no, I know. You cannot really solve it by.
So put it very close. Very close. But there is area. All this area divided by D. If D is small, A is big. So capacity is always has microscopic sizes. Here it has L squared, here it has L squared, and here it has L.
All of these dimensions.
This is something that's solved exactly.
No, don't write for us. Don't write for us. Don't write it. I read your, I know what your print is. What you have used it already is very small.
And
Yes.
this is what they're over this.
Which is the real solution.
Because of the integral.
This is your example. This is your equation 7, which is even very early. I'm talking about proposed. I'm talking only about equation 7.
This type does not happen.
C is dimensional level. Check. E squared over energy is level. Because energy. Each gap and this is your result.
You're
This is
not
your equation 7. This is blank. You know the capacity is always there.
And it's and it's called.
No, that is AP. No, I then L.
Is that
Well, much larger than this. So, this much is multiple P's. Doesn't include anything you said out. But there is not really one here. But I mean, the regulation, I'm saying that you. Correct information. It's much smaller than. Is right. It's not measured.
Well.
Bigger one. There's nothing to choose. What about it? Because I really believe in. Okay, let's take it.
Nearby, yeah. Others something like sweet green. It's both healthy and economic. And also some some salads. So yeah.
But L. That's what I said. So, yeah, it's an L.
But it's allowed.
Which is much bigger and it's not changeable, and L is never known as this accuracy. So we cannot subtract even L, it's never known as this accuracy. L, that's not pieces are not known as this accuracy. Not all capacities. You raise some, what is capacitance without some? I'm saying it's L times lower. If I have just two times of length L and distance L. So this is distance L. And stripes when you throw L. That's the question was you calculate capacity between such things. What is looking? The line operation this capacity. This is not plain, but Q. Then capacitance level. And this, and each size is L, and distance is L, capacitance is L. Okay. It's later, I wanna, it's not Gaussian system, but if we wanna see, that it's absolutely problem. I think what's very small. What you say? They're exactly illusion. Material, which you can build, has massive which compared to that. So I cannot even measure. Yeah, I'm experimentalist man. I'm stop experimenting. I took it out, they don't measure. They cannot measure. It's not measured.
Yeah, so what I'm, so this is our size, like.
Oh, this is not touching your.
No, this is not.
Just.
So
Everything is correct.
everything is right. But I don't think what I'm not doing is this. But I'm not doing.
Science calculated and result is your series. And I'm saying.
So what you're saying is.
Original one.
Is the positive, is coming. So that's one.
It's much bigger. Normally. Steady. Now the eyes slow. Yeah. So I'm warning you about this and you'll know this. Do this here. No, but you should know.
I don't agree with the non-measurable. This is necessarily not the same.
How can it be measurable? When you never know sizes of experimental things. It's accuracy. I'm sorry.
Спасибо. Самое важное, что кликер проснулся. Это самое важное.
No, they don't understand. This is a factor to it. Normal electricity is a factor.
Is the microphone? It sounds working.
Let me get my stuff.
It seems to be working.
It's a sound. That's why I'm just making mistake.
Is she not coming back?
No, she's.
Oh. Right, it's different hours. No, we will not take it. Take her spot.
I'm around and go. We can do.
I think there's some that was right, but this one.
will fit. Thank you. Yeah. We're starting from a clean level, especially we're doing the whole RD flow at the high energies. We have those models too, I think. Yeah, yeah.
Okay, we continue. Next topic is Esterlis, consent. Two-dimensional electron gas and nearly frozen quantum liquid.
I'll do my best. Okay. Okay, thanks, Andre, and yeah, thanks very much to the organizers for inviting me to this very interesting meeting. Also, special thanks to Erez for introducing many of the things that I will be talking about in his talk. So today I want to tell you guys about the two-dimensional electron gas, some new results. Oops, that's not good. Okay.
Yeah, move it a little bit down.
Okay.
Yeah, yeah.
Move.
A little bit.
Okay. Yeah, so yeah, I want to tell you guys about some new results concerning the phase diagram of the two-dimensional electron gas and how that points to a picture of the electron gas in the most interesting range of RS as a newly frozen quantum liquid. So I'll explain what I mean by that. So, okay, again, as Erez already told us, so the two-dimensional electron gas is probably the simplest many electron interacting system to write down and explain. So I'll just do that explicitly. So this is the Hamiltonian I'm interested in, just quadratically dispersing electrons. Interacting by long-range Coulomb forces. So in addition to describing the behavior of non-relativistic electrons in vacuum, this is of course the right Hamiltonian to start with if you want to understand the state of lightly doped semiconductors, where m star is some bandmass and epsilon is the dielectric constant of the environment in which they're living. Good. So with a simple rescaling of coordinates, if one measures distances in units of the average inter-electron spacing A related to the two-dimensional density by this relation, then the Hamiltonian takes on a particularly simple form. So all the material parameters factor out into some effective Rydberg of the semiconductor, and then you get in these curly braces a simple Hamiltonian that depends just on this one dimensionless parameter RS. Okay, and RS, okay, it's conventionally defined as the ratio of the typical inter-electron distance to the Bohr radius, but maybe more physically, you can also express it as the ratio of the average Coulomb energy to the Fermi energy. And what's important is that this RS scales as 1 over the square root of n in 2 dimensions, which means that the low density limit is the strongly interacting limit. The weakly interacting limit is the high density limit. Okay, and you can see that from these two terms, right? That large RS, the Coulomb energy dominates, we get a crystal. At small RS, the kinetic energy dominates, and we get some kind of Fermi liquid phase. So let me just sketch for you a schematic zero temperature phase diagram of the 2-deg. Again, kind of piggybacking off what Erez already told you. So again, we have one dimensionless parameter. You can phrase it in terms of the density. This is our one tuning parameter. So at sufficiently high densities, the system is essentially some kind of electron gas. So in this regime, when RS is small, some combination of RPA and Fermi liquid theory is probably a reasonable way of thinking about the problem. And then at very low density, the system crystallizes to the so-called Wigner crystal phase. In 2 dimensions, that crystal turns out to be a triangular one. And the best Monte Carlo simulations, like those in this paper, tell us that that transition between these 2 phases happens at a value of RS of roughly 30. And what's important about this number is not its precise value, but rather that it's big. Okay, so what that means is that there's a bit regime of density or RS where the system is best understood as some kind of strongly interacting electron liquid. Okay, and just to kind of illustrate that in what I think is a really vivid way, Here I plot for you the pair correlation function as a function of interparticle separation. So this G of R tells us the probability of finding two electrons at distance R apart. So the red curve is kind of deep in the gas regime. When RS is small, you see it's essentially featureless. At very large RS, when the system is crystalline, you have these sharp peaks associated with the crystalline order. And at intermediate RS, when the system is liquid, you nevertheless see these peaks that tell you that there is some kind of strong local propensity towards order. These charge correlations are strong. And this kind of behavior is in fact, ubiquitous in strongly interacting liquids. For instance, if you look at water at ambient conditions, then it has a very similar structure in its pair correlations. And here, I've drawn kind of arbitrarily some value of RS where you cross over from what is more like a gas to what is more like a liquid. Okay, so this system is old, it's well studied, but nevertheless, interesting questions remain. So among those, one might wonder, are there other intermediate phases that might appear? What is the nature of magnetism? So that's the kind of thing that I'll be interested in. And okay, you might wonder, can we really say anything new about the behavior of the 2-deg in this intermediate RS range? So contrary to what was believed 30 minutes ago, I'd like to tell you that the answer is yes, that there is experimental evidence of new intermediate, well, at least one new intermediate phase, maybe phases, and that the behavior in this regime, this strongly interacting electron-liquid regime, is quite rich. And there's a lot of, I think, interesting physics to be explored there. So I'll be telling you about experiments and then some theoretical ideas that were inspired by those experiments. And then I'll conclude by highlighting what I think are some routes to new physics in this old and simple, seemingly, system. Good. So, okay, this work was done across many collaborations with many people. So the story that I'll tell you started back in 2021 with two experimental papers, this one and this one. So the first paper was done in the lab of Itachi Imamoglu at ETH Zurich. And it was led by this postdoc, Tomasz Smolenski, and this was the kind of theory team that to understand the data. At the same time, there were experiments at Harvard in Hong-Koon Park's lab, where they looked at bilayer two-dimensional electron gases. So I'll mention, well, that was kind of what started all this. And then more recently, there's this work that I'll be talking about. So observation of an electronic microemulsion emerging from a quantum crystal liquid transition. That was also experimental work done in the lab of Hong-Koon Park and led by these two postdocs, Jiho Sung and Joy Wang. And also be telling you about some theory work that was mostly led, well, actually pretty much exclusively led by Kyung-Soo Kim, a grad student of Steve Skivelson's at Stanford, who is now on his way to a postdoc at UIUC. And also mentioned some work in progress with this gang, Mitsa Videvich, Sekun Zhuang, and Sasha, one of the organizers. Good. So I guess I didn't maybe say it explicitly, but part of what has led to these new insights in this seemingly simple system is really a lot of progress in experiment. So new experimental platforms in which to study two-dimensional electron gases, and also new probes by which to analyze its properties. And so let me just very briefly tell you about those systems. So the systems are these two-dimensional transition metal dichalcogenides. There's by now many of these, many families. The one that I'll be interested in is this so-called MOSE2, molybdenum diselenide. And so for the purposes of this discussion, what we need to know is that these are two-dimensional direct bandgap semiconductors with this hexagonal lattice structure shown here. So it's like graphene on a honeycomb lattice, but with an inequivalent A and B sublattice. Molybdenum on one sublattice, selenium on the other. And so the effect of this broken sublattice symmetry is to open up gaps at the Dirac points, K and K prime. The other difference with graphene is that these are materials with strong spin orbit coupling, but of a very simple kind, a so-called Ising spin orbit, which just basically acts as a valley-dependent Zeeman field that spin splits the bands in these two valleys. And in MOSE2, at least, this spin splitting is quite big. It can be on the order of tens of milli-electron volts. And so what I'll be interested in is basically these two bands. So when the system is gated, you can put electrons, say, in these two conduction bands and form a nice model two-dimensional electron gas. Okay, and what makes these systems useful for the study of 2-deg physics is that they're kind of naturally very strongly correlated. So for instance, if you want to get into the regime RS bigger than 10, then because of the band mass and the dielectric of the HBN that sandwiches these things, you need densities less than, say, 10 to the 12th per square centimeter. This is in contrast to more conventional 2-deck systems like gallium arsenide, where to get into the same range of RS, because of the smaller effective mass and the larger dielectric constant, you need 2 orders of magnitude lower densities. Okay, so what this means is you have to, you can worry a bit less about disorder effects. These systems are just naturally very strongly correlated. The thing that I would like to talk about, but I don't have enough time for, is that part of the insights that have come is that there are kind of a unique set of experimental probes by which to study these TMDs. These are new types of local optical probes, and I think a lot of the new knowledge has come from precisely these new types of experimental ways of probing the systems. And if there's interest, I can talk more about that later. So very good. So what is now the status of the phase diagram of the 2-deg as we understand it based on measurements done in the last year? So again, this is the phase diagram of the 2-deg based on optical measurements on monolayer MOSE2. Okay, this is a density temperature phase diagram. If you want to convert density to RS, that's on this top axis here. Okay, so there's a lot of things going on here. Let me walk you through it. At small RS, high density, the system is what is most likely some type of Fermi liquid. And at the lowest densities, the system is most likely some type of Wigner crystal based on these optical measurements. So this Wigner crystal phase is inferred from, roughly speaking, an optical method to extract the ordering wave vector from reflection spectroscopy. But what is new now, in addition to these expected liquid and crystal phases, well, let me start first with this big blue region. Okay, so this big blue region is what appears to be a new phase. I'm calling it a microemulsion phase. The reason for that is because it has, broadly speaking, the characteristics of some kind of mixture between liquid and crystal, hence the term microemulsion. And these data points, you see there are different types of symbols. These are different types of optical measurements that indicate some kind of anomalies as you transit into this intermediate blue region. And so what makes this blue region so interesting is that on the one hand, if you have a first order liquid to crystal transition, you generically expect some window or region of 2-phase coexistence. But these are systems with long range interactions. Okay, long range Coulomb forces don't like macroscopic phase separation. The Coulomb energy penalty is too big. And so you expect that is resolved, that so-called Coulomb frustrated phase separation is resolved by some kind of mesoscale phase separation with some kind of interesting, potentially intermediate length scale structure. So, all of that has not been yet fully characterized in these experiments. What is clear is that there are anomalies that signature indicate transit into some kind of new phase of matter, and that the kind of gross characteristics are those of some kind of 2-phase coexistence.
When you say anomalies, sorry.
Yeah.
What do you precisely mean by?
I'll show you. Yeah, I'll show you actual data.
So are you claiming that the system is like glassy even in a completely pure sample?
Well, I don't know about glassy. I mean, it's possible that this is just some kind of, well, I'll come to disorder too, but yeah. So if we idealize the system as clean, perfectly clean, then this, this kind of microemulsion could have some other, I don't know, stripes, bubbles, some other kind of intermediate length scale structure, potentially. So that's, one possibility. But some kind of glassy physics is also possible, indeed. Yeah.
Is there some correlation functions that you can associate with different phases?
Well, so in the crystal phase, ideally, you just have symmetry breaking. Yeah, here, I mean, well, in the experiment, yeah, it's hard to.
I mean, theoretically, if you say microemulsion, I just want to understand what it means.
Yeah, so in principle, there would be some correlation function that you can measure that would indicate, some type of long range order due to some kind of, intermediate length scale structures. Right? I mean,
non-exponential.
Exponential.
Non-exponential.
Yeah, I mean, long range order, not exponentially decreased. In principle, I mean, but so I'll show you data that explains what I precisely mean. I don't know what's going on, really on the meso scale, but grossly, the measurements look like some kind of admixture of liquid and crystal. That's the statement. Good. So yeah, I'll show you precisely what I mean by anomalies in 1 second. There's one other region here that's in green, liquid with enhanced susceptibility. This does not appear to be a phase in the sense that there are no clear anomalies as you transit from the white to the green, but there is a qualitative change in behavior, namely, the spin susceptibility acquires a temperature dependence that you would not expect for a simple Fermi liquid. So yeah, to Andrei's point, let me just show you now some data. So there's different types of measurements. The simplest one to describe is probably the spin susceptibility. So this is spin susceptibility. Let me focus first on this panel, okay? This one. There's spin susceptibility as a function of density for various temperatures, okay? So let me focus on this top blue curve. And so what you see is that as you increase the density from this low density Wigner crystal region, there is a very pronounced kink or dramatic, I would say, change in slope, right? That is telling you that something serious is happening, okay? And as you raise the temperature, go from blue to red, you can track this sort of kink and trace out what is some sort of phase boundary. Okay, you can plot the data in a different way. This is just taking the same data and multiplying it by temperature, a different way of viewing the same data. And then you can identify other kinks, okay, other breaks in slope that you can then track as a function of temperature to trace out a phase boundary. So this is what I mean when I say anomaly. I mean some kind of dramatic feature that is maybe in some idealized way would be some non-analyticity, of a thermodynamic observable. Good. Is there anything else I want to say about that? So very good. And so this is the circles, this spin susceptibility, there's other types of measurements that also indicate some kind of dramatic change in behavior. And what's noteworthy is that these different observables all line up on a sort of common phase boundary. So that's, additional evidence that what is happening here is really some kind of phase transition. Good. So there's some other things that I'll tell you about. So we've kind of revisited what were believed to be simple aspects of this problem. For instance, the Wigner crystal. I'll give you some arguments a little later that even this crystal phase might be more interesting than we previously believed. Namely, it might be, in fact, a metallic state of matter. And finally, let me just show you some very recent data that I was not involved with, but it's beautiful. This just appeared on the archive a few weeks ago. This is STM data from Fang Wang's lab at Berkeley that has imaged in a similar system this low density Wigner crystal that is evidently not perfect, it is disordered in some way, but to the best of my knowledge, these are the first actual pictures of this Wigner crystal phase in an electronic system. So, okay, yeah, this is the archive preprint if you're interested, and I haven't fully digested this data, so I don't have too much to say about it. Good. So yeah, so the interesting thing is a new phase, right? We want to understand it. I don't understand it yet, but I've been trying to. And so what I'd like to tell you is at least how we're thinking about approaching this phase, okay? So let me start then with the following. I'd like to argue for you that at large RS, where all this interesting physics is happening, the electron liquid is nearly frozen in the following sense. So when RS is big, the largest energy scale in the game by far is the Coulomb energy, okay? And so the electronic motion at large RS is of the following sort. We can imagine electrons trapped in some sort of local equilibrium positions in which they rapidly wiggle around, vibrate at a frequency omega dBi that's on the order of the dBi energy of the solid phase, okay? If you estimate just by dimensional analysis, what is the order of magnitude of this dBi frequency, it's on the order of the square root of the Coulomb energy times the Fermi energy, the geometric mean. And if you wish, this is also just the frequency of local plasma oscillations in the system. Now, at longer time scales, the system remembers that it's liquid. Okay, so there's some other time scale, tau, on which the electrons can tunnel out of their local cages and flow. Okay, and this time scale, or the rate associated with this time scale, tau inverse, is much, much smaller than the corresponding dBi frequency at which they're rattling in these cages. Okay, so what I mean by nearly frozen liquid is the following, is that there is a hierarchy of energy scales that looks like this. Okay, the Coulomb energy is the biggest. You have the dBi energy, or the plasma energy, if you wish, and then this call it this escape rate associated with the ultimate flow of the electrons that makes the system liquid. Okay, and presumably a reasonable proxy. Well, probably this escape rate is a reasonable proxy for some kind of renormalized Fermi energy in the system. Okay, so I'll be using this EF star to mean the kind of bandwidth that's associated with the ultimate escape of these electrons from their equilibrium positions.
This is not a single electron thing, right? It is probably some collective motion of the electrons, right?
Yes,
So-
it is. Yeah, this is a cartoon. Indeed. I mean, it's, this escape is probably, indeed, all the electrons have to move apart and move together in some way to make it more interesting. This is a cartoon. What is precise is this hierarchy of energy scales that exists. Yeah, the cartoon is, artistic rendition, but the hierarchy is there. Okay, and this picture of
Intended to indicate that there's some disorder that you have.
no, well, kind of. I mean, no, not explicit disorder, but indeed, on short time scales, probably the system does look kind of amorphous or glassy in this sense. Yeah, that's right. Good. So this perspective on liquids is not new. It goes back to Frenkel in 1946, thinking about classical liquids, and then it was revived by Castaing and Nozières and thinking about helium, in fact, helium-3. And then also by Boris Spivak and Steve Kivelson. So every few decades, this kind of picture reemerges. I think it's also implicit in many people's studies of two-dimensional electron gas, Boris included. So I think many people have this kind of picture in mind. So what I want to do is take this picture seriously. Okay. So you can ask, are these just words? Are there any definite implications of this kind of viewpoint on the liquid regime of the two-dimensional electron gas? And so what I want to argue for you is that indeed there are implications. So the simplest one to state is what this implies for magnetism. Okay, so for large RS, what is known is that the spin susceptibility is big. Okay, as compared to the non-interacting Pauli susceptibility chi naught. So here I plot for you experimental data of the spin susceptibility measured in these same optical via these same optical measurements on MOSE2. And here there's also a theory curve from quantum Monte Carlo. They agree. That's nice. But what's important is that the spin susceptibility is big. Okay, down at the lowest densities, and this is all in the liquid regime, the spin susceptibility is as much as 15 times larger than the non-interacting Pauli susceptibility. And there are two ways to think about this. On the one hand, you might say, okay, this is a system that's close to a Stoner instability. Okay, it's near a polarization transition. There's another rationalization, which is that it's nearly frozen. Okay, if a system is nearly frozen, that means the electrons are strongly localized, and this will tend to decouple the spins. Okay, the spin susceptibility of free spins is big, okay, much bigger than it is in a Fermi liquid. Good. So, very good. So again, this is maybe a perspective. What are the implications of this? So the implications we can see like this. Okay, we can ask, so the susceptibility tells us about the response of the system to small fields. We can also ask what happens at big fields. Okay, so to analyze that, let's imagine that I just kind of schematically write down the energy of the system as a function of magnetization like this. Okay, probably it's a more complicated dependence, but this will illustrate my point. Okay, so here M is the magnetization, E is the ground state energy. So at a Stoner instability, we know what happens. The quadratic coefficient goes to 0. That is, the spin susceptibility diverges, but the higher order coefficients, like B written here, presumably remain order 1. Okay, this means that the critical field to fully polarize the system is on the order of the critical field of the non-interacting system, right? You have to rearrange states across the whole band to fully polarize the system. On the other hand, if the system is nearly frozen, then that implies an overall depression of the energy scale associated with magnetism. So all of these coefficients are getting small. Okay, A and B are all going to 0, and the higher order coefficients. And this means that the critical field to fully polarize the system will be much, much smaller than it is for the non-interacting system. Okay, and indeed, this is what's observed. Okay, so again, same data set that I've been showing you. This is the critical field as a function of density. Okay, here I don't have RS on the top axis. This is in the range of RS, roughly 10 to 15. And what they observe is a critical field that is indeed 10 times smaller than the critical field that you would need to polarize the non-interacting system. Okay, so to my mind, at least, this is pretty compelling evidence that the system is indeed nearly frozen in the way that I was describing. Yes, please.
So what is temperature in this?
Yeah, so this, good. So I don't remember for this exact plot, it's on the order of 1 Kelvin, which is much less than the Fermi energy and all the other energy scales in the problem. Yeah. Yes.
So just to make sure, you have a situation where on one hand susceptibility diverges, on the other hand polarization is almost instantly larger.
No, I mean the susceptibility is big.
Okay.
Yes. Yeah, that's right.
Yeah.
Yeah, please.
So you have an estimate for this
energy scale h bar over tau that you had? Is bigger than-
Yes, yeah, I'll show it at the very end. I have an estimate. I mean, a crude estimate
Is that
from
bigger than temperature in this starting?
smaller, even smaller.
Even smaller.
Even smaller. Yeah, yeah. So this, so this temperature is smaller than the bare EF. Yeah. Yeah. Oh, sorry. Now I understand. I was thinking backwards, but yes, it's still smaller. Temperature is still smaller. Yeah. Good. So, so this suggests that one way to think about this. Oops, sorry. Interesting new phase, maybe even phases. To try to understand them is to, to understand the properties of this liquid is to start from the solid phase. Okay, so we are used to thinking about liquids starting from some kind of imperfect gas description. What I want to advertise is that maybe we can gain some insight by starting instead from the solid. Okay, if the system is nearly frozen, then this might not be an unreasonable way to go. Good. So to do that, let me start with the quantum mechanics of the Wigner crystal. Okay, so one way of quantifying quantum effects is to think about the 0-point vibrations of the Wigner crystal phonons. So if you do some dimensional analysis, you find that the RMS fluctuations, the ratio, excuse me, of the RMS phonon fluctuations to the lattice spacing scales with RS in this way. Okay, that means at large RS, this ratio is small. The electrons are well localized to their Wigner crystal lattice sites. And upon increasing the density, that is decreasing RS, they spread out. Okay, and eventually, in fact, this spreading can become on the order of the lattice spacing. So if you do a slightly better calculation, taking into account the full phonon spectrum, then you find that, for instance, when RS is 60, this ratio is roughly a quarter. Okay, so the implication being that the overlaps between these localized orbitals are significant, appreciable. Good. And so when you have significant orbital overlap, you also have significant electron tunneling and delocalization. Okay, how am I doing on time? I forgot.
You have about 5 minutes.
Okay.
Then questions.
Okay, I should be okay. Very good. So what are the implications then of this electron overlap? And when does this become important? Well, we heard about this a little bit during Erez's talk. It has implications for the magnetism of the Wigner crystal. So in the purely classical limit, Wigner crystal has a massive degeneracy associated with putting spin up, spin down electrons on all the different lattice sites. That degeneracy is resolved by quantum effects. So by these sorts of ring exchanges that I've shown here, and they can be computed by some instanton calculus or WKB-like calculations. And so you could think that, as RS is getting smaller, as the overlaps are getting bigger, these effects are becoming important. But okay, so it's an important effect in that it lifts the spin degeneracy, but it's likely irrelevant in practice. So it turns out that these actions, these dimensionless actions that enter into the calculation are big enough that even when RS is near melting, these exchanges are very small, and so it's not very interesting. There's a more interesting angle on it, which is when you think about the quantum mechanics of point defects in such a crystal. So classically, of course, the creation of a defect costs energy. Okay, so the cartoon, here's a vacancy, here's an interstitial, the two simplest point defects. But when you allow for quantum tunneling, which we're saying becomes appreciable when RS is getting smaller, then that can lower the energy. Okay, the defects can delocalize and that will lower their energy. And then you get into an interesting situation where as you increase the density or decrease RS, you get a defect band. Okay, they get a finite bandwidth, which is on the order of the hopping or the tunneling rate. And the interesting thing that can happen is there can be a critical density at which the bottom of this defect band falls below zero energy. Okay, and this would imply then that you get into a state with a finite concentration of such ground state defects. Okay, this is not an original idea. This goes back to Andreev and Lipitz in 1969 when they were also thinking about helium. And so in the present context, such a defect Wigner crystal in which you spontaneously nucleate a finite number of ground state defects would be a distinct phase of matter. It would be a metallic charge density wave state. So there was a question about these Overhauser CDWs. This is something like that, but coming at it from a strong coupling perspective.
Yeah. Why isn't there an issue with Coulomb repulsion, like you said at the beginning? So these defects, if you lower the density of your bulk phase, they need to go to the boundary. So why isn't there a problem with the Coulomb?
Why do they need to? I mean, here what I'm telling you is basic. So maybe I can say it a different way. This is a charge density wave phase with a number of electrons per unit cell that's different from 1. right? That's all I'm saying. I don't know. Yeah.
In this Andreev-Lifshitz construction, right?
Yeah.
Once you create these vacancies, right?
Yeah.
You lower the bulk densities.
Yeah.
Density, but then the rest, these other extra densities at the boundary, right? Am I remember correctly?
So
Which seems to be
I mean, okay, I think
Coulomb
probably
energy.
there's multiple aspects of that story, but here I'm describing something I think simpler, right? Which is if you can ask, if you form a charge density wave, what is the number of electrons per unit cell? And so deep in the strong coupling limit, when the system is highly classical, you'd say you have to have one. But as the system becomes more quantum, then a priori there's no reason you have to have one. That's all I'm saying. It's just a CDW, a metallic CDW. So from the kind of Fermi liquid side, that wouldn't sound crazy, right? It's just a metallic charge density wave, but viewed from a different angle.
Finish in a couple of minutes.
Okay, yeah, please. Good. So we've tried to calculate whether such a thing can happen. We do it by this kind of, we means Kyung-Soo. So he's calculated by this kind of instanton calculus the tunneling rate of defects in Wigner crystal. And indeed, you find that if you compute the energy of, say, an interstitial, okay, which is the Coulomb energy, plus some 0-point energy associated with the phonon fluctuations, and then a kinetic energy coming from these hoppings, then indeed you find that energy goes to 0 at some finite and relatively large value of Rs. So this is the energy, the red curve is the energy of an interstitial as a function of Rs. And you find that, in these calculations, it goes to 0 at an Rs value of roughly 70. Okay, so that is larger than the Rs for the melting of the crystal. So it's suggestive that, in fact, in a broad range of Rs, especially the one that's relevant for experiment, the Wigner crystal might be, in this sense, metallic. Okay, good. So that's this region here. So metallic electron crystal. Okay, since I'm running out of time, let me skip, unfortunately, this part, but good. So now we can just ask, is there anything else in this phase diagram? This is where I'll end. So I've shown you, this nice phase diagram that I'm very excited about, but we can ask, what happens as we increase the density, raise the temperature, and is there anything else in this phase diagram worth exploring? So the answer, I think, is yes. And to see why, let me come back to this picture of a nearly frozen liquid. Okay, so this is the same cartoon, electrons that are localized to certain equilibrium positions. They rattle around in their cages and then they flow out. So we said that this kind of picture is rationalized by this hierarchy of energy scales. And now we've been up to now mostly talking about kind of low temperature physics, but you can ask now, where can I put the temperature, okay, within this set of inequalities? And there's a very interesting regime where I put the temperature below this Debye energy, but above this renormalized Fermi energy. Okay, and this regime has been, proposed before, again, by Andreev. Okay, he did a lot of good stuff. And then again, kind of thought about again by, of course, Spivak and Steve Kivelson. And so the idea then is that there's some temperature range in which the system is semi-quantum. Okay, in the sense that you're at temperatures above the degeneracy energy or temperature of the electrons, but still below the Debye frequency of these phonons, or however you want to think about it in this liquid phase. Okay, and so you can ask, how big is this regime? Is there any interesting physics to be observed here? And what I want to tell you is that it's big. Okay, so here I'm plotting a phase diagram, 1 over Rs squared and temperature. So 1 over Rs squared scales with the density, so that's why I plotted it this way. And okay, Rydbergs are not very useful. So if you translate, for instance, in gallium arsenide, a Rydberg is roughly 100 K. In TMDs, it's roughly 1,000. So you can convert this axis to Kelvin if you want. And here I've estimated this renormalized Fermi energy by the spin susceptibility. But in any case, the point I want to make is that this semi-quantum liquid occupies a huge chunk of the two-dimensional electron gas phase diagram. So good. So I should have blown this up, but to put that in perspective, the phase diagram that I was advertising up to now is down here. Okay, this other region, this semi-quantum liquid, is everything else. And this, as far as I know, is terra incognita. That's what is happening here. So, if we're lucky, maybe there'll be unicorns or some other interesting things here to explore. So, I want to advertise that there's a new type of quantum liquid that is occupying, a big chunk of this phase diagram. And I think it's worth studying. And this is something that we're thinking about now. So if you've done numerics, then something that kind of goes off in your mind right away is that when the temperature is above the degeneracy temperature of the fermions, then you no longer have a fermion sign problem. You don't care about the statistics anymore. And so you can hope to really crush this problem by numerics. And so that's what we're doing now in collaboration with Dave Sepperly, using some of his path integral Monte Carlo simulations to try to really understand what is going on in this region of the phase diagram. Okay, so with that, I'll conclude and thank you for your attention.
Let's start from that side.
Yeah, to better understand your novel emulsion phase, could you
Yeah.
please plot the static structure factor as a function of momentum?
Well, that hasn't been measured, so I don't know. Yeah, I wish, but yeah, we don't have access to those kind of observables yet.
Yeah, so, so this frozen liquid. State, the helium-3 conflict is large literature where people called it an almost localized Fermi liquid.
Yeah.
So,
It's similar. Yeah.
Basically the same thing.
It's in the same spirit. Yeah, that's right. Yeah.
But there's one thing from there that may be pertinent to what you're talking about. So this question of whether the enhancement in susceptibility is Stoner or localization.
Yeah.
So there's a criterion as so in helium-3, if you as a function of pressure, if you measure the spin susceptibility and the heat capacity, right? So the Wilson ratio, doesn't change.
That's right.
Right. So the increase of chi is coming just from mstop.
That's right.
Okay. So so there's a question here. Then perhaps you can have a more direct proof.
Yeah.
If you have a measure, you meaning your experimental friends.
Yeah.
Have a measurement of mstop, which is hard, of course, but you could imagine either from Shubnikov de Haas, or from thermal power.
Yeah.
Right, which may both be feasible.
I suspect that the Shubnikov de Haas is something they'll try. They just, the trouble that these materials, because the densities are high, you need really big magnetic fields. And so, that makes it, but I suspect that this is something they'll try to do.
But what about specific heat?
That's they
it's a
can.
2D material. Right?
Specific heat is probably
hard.
Although, one thing that I want to advertise, so I didn't get to talk much about the actual experimental probes, but these optical probes are very rich. And I suspect that, with a little bit of creativity, we could think about ways of extracting other parameters of the system from those optical measurements, in fact. I can offline, I can tell you about what those measurements are, but I think they have a lot of information in them that we need to figure out how to extract.
Yes. Can we rule out the possibility that at low temperature, the whole microemulsion phase is kind of smearing or like the intermediate phase between liquid crystal and Fermi liquid is a result of disorder?
Yes, very good question. So no, but the argument that I'll give you that the reason I don't think it's that is because these anomalies, and there are other anomalies that I can show you, are very sharp. So indeed, I mean, the first thing you might think is that, this big blob is just a rounding by disorder of a direct transition. But, these features, to my eyes, are quite sharp. This break in slope, this break in slope.
Standard deviation, the bar, they are also quite big.
Yeah, that's true. But there are other measurements. So I can show you other data. Sorry, maybe I'll show you after. But they have lots of, I showed you the simplest observable. But there are different symbols here. And they're all different types of measurement, and they all show very dramatic features. I'd be happy to show afterwards. Yeah.
Because one comment is that naive estimate of disorder impurity concentrations. Also a few times 10 to 11.
Yeah. So
it's roughly the same range.
Well, so that's debatable, I would say. So indeed, so people have tried to estimate. So the challenge with these TMDs is it's hard to do transport. That's the conventional way we probe 2-deg. So it's hard, for instance, to get like a residual resistivity, which is one metric for disorder strength. So in a transport measurement on a 2-deg, you measure transport across the whole sample. You care about the whole sample. In these optical probes, they go to one spot, a few micron size spot. Then they go to the best spot on the sample, and then they see interesting physics. So presumably, these. Yeah, exactly. So they do see, I wish I had more time to discuss that, but there are spot-to-spot variation in the sample. So presumably all this interesting physics is, I would think, in some region where maybe the disorder is in fact weaker. But to systematically study that would be very interesting.
Could you show this the picture with the optical image of this microemulsion?
Oh, yeah. So this, sorry, yeah. This is what they call a crystal, actually. But I haven't, oh, sorry, I'm going the wrong way. Yeah. Sorry. Oops. Yeah. Yeah.
So my question is about what is the length scale, the inter-electron spacing, and perhaps it's related to Dima's question on charge neutrality. If these are macroscopic inhomogeneities, then how do you think of them?
Yeah, so indeed. So let me not comment too much on these experiments because I haven't digested them. I wasn't involved, but I think it's very interesting. So these inhomogeneities, that's actually what makes it interesting, right? If it was macroscopic inhomogeneity, then Coulomb would penalize you for it. So presumably, well, what I think would be happening, and that's what was actually proposed by Boris and Steve, is that resolution, the resolution between this intrinsic tendency towards phase separation and the Coulomb energy penalty is some kind of intermediate length scale ordering.
But these are microns, right?
Yeah. So this, I mean, I don't know much about this experiment. So I agree. And this is confounding. I mean, they say words in this paper that I don't understand. So I just wanted to show it because it's pretty, but I don't quite know what's going on here.
Yeah, at the level of the materials, at the level of the materials, MOSC2, you said that the conduction band is at K and K prime, and there's some Berg curvature there compared to gallium arsenide.
Yeah.
Do you know in which regime you may see effect of that, or is it because the system is too good?
Yeah, the honest answer is I don't know. I think at these low densities, I'm not sure if it plays a role, but I haven't thought about it at all, so I shouldn't comment. Okay.
Is there a chance they do? Sorry. So you mentioned that part of the picture is that these systems can shake around to their local minimum.
Yeah.
Can you comment on what you think would be the excitations of the system if you presumably A is not a good quantum number, but you could.
Yeah, so yeah, I mean, maybe my picture is a little misleading. So this is still a translationally invariant state. I'm kind of giving you a cartoon for what is maybe happening locally on short time scales. I think, I mean, yeah, the system is, still, there's no symmetry that's broken yet. The excitation spectrum, I mean, presumably you might think that it's sort of similar to a glass, kind of the way you have in two-level systems. Although I don't know for sure. I mean, that's something that I'm interested in studying now, in fact. But on the other hand, it could be that this is just a perverse way of describing a Fermi liquid. So it would have, a priori, I don't think that this is in conflict with some kind of Fermi liquid description. So it could also have many of the characteristics.
One over tau that you introduced, would it be just viscosity of that thing if it exists? It's just viscosity.
Yeah, exactly. Yes.
So it flows.
It flows. Yes. Right. Yeah.
Okay, very quick question about susceptibility. What's your prediction for chi of Q? If I take non-zero momentum, also question, is it possible to measure it? Because I think in the case of frozen, chi should depend on Q. In the case of its speed susceptibility, then chi should be very much big that Q equal to 0.
Yeah, that's a very good point. Sort of similar to the same argument.
Chi of Q omega or chi of Q0?
Chi of static chi of function of Q. Chi of omega is also interesting, but it's separate.
So experimentally, I don't see how they can measure it, at least anytime soon. Maybe, but yeah, maybe. People have computed it in these quantum Monte Carlo simulations. I don't remember what the structure is. We could look at it. It has been computed. Yeah.
Okay, there is some time. Thanks very much. Last talk this morning for the Crépel, excitation mechanism for superconductivity in multilayer 2D materials.
Right. Thank you for the introduction. I should thank Jim Simons actually for two things, for allowing this conference, but also for paying my rents. So I'm from the Flatiron Institute. I want to talk about the charge transfer exciton, mechanism for superconductivity in low dimensions. And the two pieces are important. So low dimension allows you to have some excitonic mechanism for superconductivity. At least that's what I will argue or recall at the beginning of the talk. And then the mechanism, specific mechanism I will show you is non-perturbative in the interaction scale, and that allows you to reach high TC. I will illustrate just on 2 materials, but these are just excuses to bring models where this applies, and then maybe talk about prospect in Moiré transition metal chalcogenides. Right, so to motivate all of that, I just want to take one example, which is zirconium nitrogen chloride. It is a wide bandgap semiconductor. Bandgap is about 2.5 eV. It has 2 pockets, K and K prime. And you can dope it by lithium intercalation, either by just a substitution or with liquid gating, allowing you to reach lower density in a cleaner setting. And what's seen is that this material superconduct with a TC between 10 and 20 Kelvin for very low doping concentration. What I mean by low density here, if you translate the density in terms of Fermi temperature, and you compare it with the actual temperature that they've just measured, the BKT one, not the T star, then you see that actually this material, the TC of a TF of this material is of the same order as magic angle twisted bilayer graphene. So it's extremely high, and it's above like all the other unconventional superconductor that lie on this greenish line here. So that's also a plot that was in the experimental paper. So yeah, they claim they have extremely high TC over TF.
But what kind of concentrations you're talking about, just in numbers?
Yes, so the concentration will be 1 part per 1,000. 1,000 unit cell. So 1 dope charge per 1,000 unit cell. Like or 2.
100.
This is 100, but they can go to 2 per 1,000. Yeah, so it's very like you dope 2 charge every 1,000 unit cells, and you see some signs of superconductivity or superfluid behavior. So it's extremely low density. That's really the claim here. But contrary to other unconventional superconductor, the parent state is extremely trivial. It's a band insulator. It has no topology in it, no protected crossings. It has weak correlation, low entropy. So basically, the only question is what is happening in this system and what can give you a polarizability to mediate superconductivity. Oh yeah, and also it was measured with Raman scattering that the phonon coupling, electron phonon coupling decreased as you were decreasing the density. So decreasing electron phonon coupling and increasing TC. So that gives an argument against any phonon mechanism. So you look for what can. Yeah.
Let's clarify one thing on that plot.
Yes, sure.
So no, the next one. So you have a box around lithium intercalated zirconium nickel on nitrogen chloride. It seems like it's way below that band.
Yeah, so that limit, so the little bump here that you see is the same little bump that you see here.
I see.
Yeah, so and that's why. So it's as you lower density, you have constant TC, lower density. So in this system, that's just a band insulator, the parent state. When you have no doping, there's still something that mediates some polarizability in your system, and that is Exciton. So can you have any excitonic mediated superconductivity? It's actually something that has been envisioned a very long time ago, a few years after the PCS theory by Ginzburg. And the first idea was just to proximitate 3D metal with a semiconductor, 3D semiconductor. And the hope was that you would increase TC by that mechanism because you trade the Debye frequency for an excitonic frequency. And the excitonic frequency, the ratio between the two, scaled like the square root of the masses of the ions versus electrons, that give you a factor 100. So the hope is that you can increase TC that way. The thing that actually Ginzburg also noticed a few years after is that the constant here is exponentially small, and exponentially small in the exciton electron coupling. And that is just the overlap between the excitonic wave function and the electronic wave function. So they made calculation in 77, and they found that that overlap was only large if you had almost only a few angstrom of a semiconductor, which was not possible with the quantum wells. But now it's really revived with all of the 2D and layered material that we have at our disposal. And the intuitive way to understand it is that if you couple a 3D exciton to a 3D electron gas, so the excitons have zero probability, the hole and electrons of the exciton in 3D have zero probability to be on top of one another. So it's very hard to put an electron on top of the hole in 3D. Well, in 2D, they already have a non-zero probability to be on top of one another. So if you add another electron, it will also have non-zero probability to overlap with the exciton. And that is just a partial wave decomposition is hydrogen atom in 3D versus 2D. Right, and this is why it can be argued that the excitonic mechanism needs to happen in low dimension. Now, something that you would like is maybe a charge 2A exciton to exist, and at least somewhere in the spectrum, and that would hint at pairing because the charge 2 exciton is basically the product between a Cooper pair and an exciton, and if you have the two orders at the same time, you hope that somewhere in the spectrum, even as a high energy excitation, you get the charge 2 excitons. That, however, does not exist in 2D for pure Coulomb interaction, and that was proved by Lieb. But as any theorem, mathematical theorem, there are physical situations where you can bypass it. So one way is just screen the Coulomb interaction to not get the 1/r, for instance, with a metallic gate. And that was actually experimentally measured in this nanolater 3 or 2 years ago, where the Q peak here, they could really characterize it as having a charge 2e, or by the intensity dependence of the dependence of the peak with applied intensity to excite the excitons. Another way to go away from the Lieb theorem is just to look at a lattice or have a finite density of electrons surrounding your hydrogen atom or twice ionized hydrogen atom. Because if you have a lattice with a constant background of charge, the excitons will be more localized just because of all the repulsion with the frozen charges. And that can allow you to get something like a charge 2 excitons that you can see here in red in some, for some interactions between the sides. So yeah, that was done in this. You can find more details in the PRB reference there. Right, so
sorry, what is charge 2 exciton? This is trion?
Yeah, so the trion would be the trion always exists. It's a charge E or charge minus E. Yeah. And then the charge 2E will just be you append another hole or another electrons to it. Yeah. But it's something that's, to my knowledge, only been seen in this experiment. And they are very careful data analysis of that peak. But you can, at least theoretically, under some condition on the lattice, also favor it. And here you can see there's one hole in the underlying charge background and 3 electrons. So that's also a charge 2E object. Right, so, okay. Right, so the ideal conditions are low dimension, ideally in a material where actually the exciton and the itinerant electrons live on the same orbitals. Yeah, and you can achieve that. To achieve this kind of mechanism, you need screening or an underlying lattice at finite density. So let me go back to the zirconium nitrogen chloride. And in this PRB, the minimal model to capture just the band gap and the topmost and conduction band and the topmost valence and lower conduction band was given by in this PRB, but it's basically just a honeycomb system, just to respect the symmetry of the material, with 2 lattices and a large trivial gap of something like 2 eV. And here I've also added the dominant interaction between A and A particle and A and B particle, A and B being my 2 sublattices of my honeycomb lattice. Right, at n equal to 2, we want the system is a band insulator. So the charge transfer energy here, delta, which has some delta naught and UA, needs to be large, and in particular large with respect to the tunneling between the two sublattices. And the parent state is just a band insulator, but in this limit of very large gap, you can look at it as just a charge transfer insulator where all of the A sites are doubly occupied, all the B sites are empty. And as you add charge to this Hamiltonian, to this lattice, they will live on the B sides because of Pauli exclusion principle. Right, and the main result is that under some condition, that relates to the excitonic structure of this system. You can get the system to have an effective attraction when you dope 2 charges only to the system, only 2. So that explains the very low density, that could explain the low density observed in the experiment. And the condition do not depend on the strength of V or parameterization of V. So you can reach also high TC by just changing this value in theory, and then you should just fit it to maybe DFT or something. Right. And yes.
BC to BCS.
Yes.
So how you?
Because you have an effective attraction all the way down to 2 dope charge in some limits, then you can, when you add only 2 particles, they form a bound state.
Yes.
And there's no really TF if you have 2 particles. So that's why you are in the BC limit.
Right. And then.
Yeah.
And how you get this? How you get actual pairing afterwards?
That's the pair. So you form local bosons.
Yeah.
To begin with, and when density is large enough so that the TF increases, then that transforms into a BCS. It's just a smooth crossover between the 2 regimes, but you have strong. But yeah.
Overlap of bosons. I mean overlap of the bound states.
Yeah, of the bound states.
Just the usual crossover.
Yeah, it's a regular one that is known in cold atom system and has been measured. It's the same, exactly the same. Yeah.
But is there evidence that actual TC scales with density, like could be in this situation, when everything is determined by superfluid stiffness?
Yeah, so for non-retarded pairing interaction in 2D, I think TC scale with the square root of density. So that's why you get eventually the BCS regime.
Well, it depends on whether interaction. Well, it depends also.
Non-retarded or yeah, it's what's the typical time scale for the interaction. I agree. Yeah. Right, and the difference, and the main difference I want to draw here is the difference between the situation on the left. You had 2 dope charge in the quadratic band. They have Coulomb repulsion, so there's only repulsion, versus Coulomb 2 particle added on top of an excitonic medium. So they can basically glue because they repel with all of the other charges. Right, and the mechanism, yeah. So just you can illustrate this, all of the excitonic effect by just looking at the 4-side cluster. So this is the same as before. Here I have a doubly occupied A side, no dope charge, 1 dope charge, 2 dope charge. In the absence of tunneling between A and B, the ground state is just shown here. It has no binding energy, meaning that the energy cost of adding 2 electrons is twice the energy cost of adding 1 electron. But then as you introduce some tunneling between A and B, all of those ground states will hybridize with some excitonic state. And the energy of the excitonic state decreases with increasing doping. So, and what that results in is that the energy reduction within second order perturbation theory of the charge 2e ground state will be bigger than the charge 1e object and the charge 0e object. And if you put actually the number in this very specific model, what you get is that the binding energy becomes positive, meaning that it is favorable to add 2 dope charge instead of twice 1 charge into the system. So you have balance keeping in this 4-side cluster. Yeah, and so that's the 4-side cluster method, but you can do it also on the full lattice. It's just that you include all of the excitonic effect the same way within second order perturbation theory, but now you need to use a different method. So the resulting Hamiltonian is this one. It is very simple. There's tunneling between the B sides now on the triangular lattice. There's a repulsion that's just the original repulsion that the fermion had on site. And there's 2 additional terms that come from the difference of energy of the excitons as they have different charges. So these are when you keep interaction during downfolding, and these are usually terms that you remove because you assume that the band you downfold has no interaction with your conduction electrons. And amongst those two charges, there's a nearest neighbor repulsion and correlated tunneling. The triangular side, that means that tunneling will be faster if you have a charge nearby. And this is the one that will drive pairing eventually. Right, so you can simply solve the model for two dope charge, compute the binding energy in all of the channel, and you see that indeed binding energy in some regime will be positive, signaling pairing. And the channel in which the pairing occurs is the triplet channel, and it looks like that on the lattice. So this is the two-body wave function. So it has an F-wave symmetry, and it is a singlet. You can also just derive the gap equation for this Hamiltonian, and you see that the dominant pairing channel is indeed triplet. It has coupling strength VF minus 2 lambda, so that's where the coupling comes from. And this thing is negative in a large part, for this set of parameters, so that you can really pinpoint. Yeah, and the spin triplet now can be simply understood as a Bally singlet. So there's a one pocket at K, one pocket at K prime. And what you have is just a fully gap order parameter in each pocket, but then a different sign on opposite side of the Breuer zone, and that is the ferromagnetic coupling between the two Bally that we heard of in one of the first talks before.
Is it F-wave altogether or not?
Yeah, it's F-wave altogether because you change sign here, there. You would have node of the order parameter along those gamma M lines. Right, and so maybe I want to also say that we did not make any approximation on V. So you can increase V and get an increase in the critical temperature if you solve the TC, so the gap equation. And there's the other thing I want to mention is that all I've said about actually it's a result of the nodes that you see here. So TC starts to increase when you have two pockets that increase in size because the density of state at the Fermi energy increase. So that's the first behavior that you see here. And at 1/8, actually the Fermi pocket becomes only a single pocket around gamma, and it starts decreasing. And so the Fermi density of state at the Fermi energy decreases. That's the shape that you see here.
Quick question. So in the BEC limit, basically you calculate the thing just.
Yeah, here I compute T star. So
what is that? Yeah.
Yeah.
What is T star?
Okay, so that TC is solving the gap equation. It gives me T star in the other
field TC.
Mean field TC. There's no superfluid stiffness at the moment.
Is it so? Does it become just the coupling energy of the binding energy of the
Exactly. Yes, that's exactly it.
Okay,
It's not the TBKT. I've estimated the superfluid stiffness also in that model.
Right, so just a particle problem.
Yeah,
Okay,
but and it's below. But okay, yeah, very good. Yeah, so the essence of the toy model is that we have a lattice where exciton and electron couple strongly. We have a charged Chewy object somewhere in the spectrum that has lower energy than all of the other exciton, and that it prints some pairing to the itinerant charge. And really what you should do is include interaction when you downfold, because it's this interaction that will give you pairing, this correlated tunneling and some pairing. Yes, low dimension means 2D, but also 1D. So I have a 1D effective example to share as well. It's a very new material that was only measured a few, or maybe a year ago. So yeah, that superconducts at 90 Kelvin. It's a corporate ladder system, and you have a ladder of say CuO2 embedded into a material, but the resistivity is really unidirectional, and it's seen to superconduct at about 90 Kelvin. The Slater, like if you take just the relevant orbitals for these materials, you can derive a Slater-Kostler tight binding, and yeah, and you can basically perform the same machinery as I was showing before. The only thing that changes is here because of the lobes, the sign structure of the p orbitals. the second order process can pick up a minus sign that will flip the sign of the correlated tunneling. And basically you won't favor triplet, but singlet this time. And you would get a nearest neighbor singlet that's you are more used to for Crépel systems. So in more detail, this is just, you can model it with the same type of Hamiltonian, do the same straightforward transformation, you get 3 terms. And again, the correlated tunneling drives pairing, but lambda is negative. So if you compute the Cooper vertex, what you see is only one of them is negative. It's the nearest neighbor singlet because it's cosine, now it's even under inversion. Right, and yeah, I just want to quickly sketch because I don't have much time, or give like weak reason and maybe also talk about other studies that says that a similar mechanism can be found in Moiré TMDs. So transition metal dechalcogenate were introduced just before, so I've removed my slide about those. And I just want to show that if you have 2 TMD with a slight lattice mismatch, they will form a Moiré structure as well. And the minimum of electrostatic energy for this heterostructure is found at the XM and MX stacking configuration. This is where a metallic atom of 1 layer is on top of a chalcogen. But because all of the electrons are carried by the metallic orbitals of the system, this state will be localized in 1 layer. And then the other minimum is at MX, and the state will be polarized in the other layer. So basically, you have a honeycomb lattice formed by the MX and XM orbitals. And on XM, you have electrons in 1 layer, MX, you have electrons in the opposite layer. And because these are, or you can tune it, but these are, you can choose it to be hetero by layer so that the system also have a difference in the gap head, in the valence band maximum. And that provides the charge transfer I was talking about. And the fact that it's really a charge transfer and not, yeah, it was really highlighted in this PRB where they put actual energy scales. So they may realize just the system we look at. The important thing we wanted to play with is that because of Ising spin orbit coupling, the SU2 spin symmetry now is reduced to U1, and you can get not at n equal to 2, but n equal to 1, interesting ferromagnetic or antiferromagnetic phases. So we identified one that we like, is that when the 2 heterobilayer are originally aligned, but have a slight lattice mismatch, you favor an in-plane ferromagnet. And so this in-plane ferromagnet only has Q equal to 0 component. So you will still favor a triplet state because of the same mechanism, but that triplet state has an emergent time reversal symmetry, and that will form a protected Z2 triplet state. The interesting thing is that the BEC to BCS crossover in that case is not a crossover, it's actually a transition. You need to close a gap because the BEC state is trivial and the BCS state has a quantum spin hole with helical Majorana mode. So that's yeah, it's just like small increment on the same theory. But yeah, in a more broader picture, I want to open the discussion and say that having a charge 2 exciton is just a closed channel in the excited state. And coupling to it can just be seen as an analog of a Feshbach resonance from the cold atom community. And this picture has really been pushed by Ataç İmamoğlu, which has 2 theory paper on it. So as you can see, there's some charge 2e object that form a closed channel. These are our molecular charge 2 exciton that I was mentioning. And when you can couple resonantly to it in some way, for us it was thanks to tunneling between A and B sublattices, then you can get some pairing in the same mechanism as cold atoms picture. Here they apply it to tri-layer TMDs, which they have, I mean, they have more knowledge of what is good in terms of material realization because they actually measure these materials. But this mechanism in terms of a Feshbach resonance to something that looks like a paired state with charge 2e has actually been revived in interest over the last few months. And I'm only quoting here 5 papers that all appeared between October and December last year, where the superconductivity in nickelates or cuprates is looked at in terms of this Feshbach type of resonance. So yeah, I don't want to put my finger into that pot, but at least there might be just some other things that we can view with this either excitonic or other kind of charge through excitation, Feshbach resonance, superconductivity. Right, and I think that's all I have to say. Yeah.
So you, in a case of the TMD heterostructure, and especially if it's a more TMD, you want to still be in a very low density limit, but we also know that sample sizes are quite small. So is there possibility for a situation that your sample at those densities will actually become a quantum dot instead of having a lot of electrons? Because there is a difference of having 1,000,000 electrons and 1,000 electrons.
Yes, so the density we look at is something like filling 2 plus epsilon. So it's not extremely small because we need to fill the, to get that picture, you need to completely deplete this band and fill it with a tiny bit of electrons. So it's actually the filling of 1 minus or 2 minus epsilon of charges. And that can be done by electrostatic gating.
Questions? So, you mentioned that in 2D, it's usually not favorable to have these charge 2 objects from excitons, but that you can get that either from gating or from lattice symmetry. When those objects form, can you say something about the matrix elements for that lead to pairing in comparison to phononic mechanisms? Because you pointed out that the excitons can be much higher energy, much higher bandwidth, so that's good. But what about the matrix elements?
Yeah, so there will be matrix element. So the charge 2 exciton will only have matrix element with pairs of electrons that are nearby because it's a molecular state with charge 2e. So you only couple to it when 2 electrons are nearby. And when 2 electrons are far apart, they individually couple to trions, say, charge 1e. So there's a balance between the matrix element that you get for each of these 2 objects separately and their energy. And that's why you need the charge 2e object to be much lower than the trion. So that even if they even if the 2 have comparable matrix element, you still gain energy by coupling to the charge 2e object. And here it's not the case. So you have the trion first and then the charge 2e. So that won't induce any superconductivity. You need to flip the order so that for the same matrix element, you will get pairing for the itinerant electrons.
Questions?
So is there any evidence for this kind of extonic mechanism, say quantum stableness or something more canonical?
At the very lattice scale, it's actually hard to say that it's due to an excitonic, like the pairing mechanism is a bit of a view of your mind or how you understand the physics. So I don't know if I have good probes. A definite probe would be if you can tune the position of that charge 2e exciton optically, like by changing the gate distance and see that it crosses. And at that point, you have superconductivity, then it might be an experimental probe that exists, but I don't think, yeah, it's actually proven that there's any. Yeah.
What about feedback from superconductivity on charge 2 exciton?
Yeah, it might repel. Yeah. If you, yeah, okay. It's true. If you have strong superconductor, if one brings down in energy, it takes two charge 2 is brought up. So didn't think about that. Yeah, sorry.
Okay, and maybe I get the last question. You mentioned that towards the end of your talk that there was interesting phase transition between DC and DCS.
Yeah.
What it is?
Oh.
Say it again.
Yeah, it's just that if you have a time reversal helical Majorana mode in a BCS state, so it's basically you have a triplet state up with a triplet state down. That's only possible if you have U1 spin symmetry in your system because you don't have the up down plus down up. they are rated by time reversal symmetry. And then in some cases, if you have like they show they are topologically ordered, which is the case for this material. We highlighted condition for that. But the BEC is like strongly bound pairs, and only the pairs flow, and the pairs are up plus down down. So there's no helical Majorana mode at the edge. It's not topologically ordered. So between the two phases, you need to have a gap closing. It's just
can it be that the BCF breaks U1, in addition to have U2? Is there any region when say U1 is unbroken, but Z2 is broken? Some preemptive phase?
Yeah, but maybe it's my so I was treating that maybe in just the mean field BCS to maybe too simple. I was not including fluctuations on top of that.
You know, I think I should make a comment because
the
fact that the notion of transition between BC, where basically it's definitely a fully gapped state because it's just, and complicated gap like D-wave gap, that it's a phase transition. There was a paper actually of Andreev and Gurari, I believe some time ago, where it was basically shown, if I remember right. The transition between a gap full state and gapless state is a transition rather than crossover. And it was for flashback resonances or something in guesses.
My recollection is
okay, fine. Yeah.
Okay, great. Thank you very much. So we convene